Look up at the night sky on a clear evening, and if you're in the southern hemisphere, you might spot Alpha Centauri, a brilliant point of light that has captivated humanity for millennia. It's our closest stellar neighbor, a mere stone's throw away in cosmic terms. Scientists speak of it with excitement. Futurists include it in their visions of humanity's expansion into space. And science fiction writers have sent countless fictional spacecraft to explore its potentially habitable worlds. But here's the uncomfortable truth that nobody wants to admit. We will never reach Alpha Centauri. Not in our lifetimes, not in our children's lifetimes, and quite possibly, not ever. This isn't pessimism, it's physics. And the reasons why tell us something profound about our place in the universe and the fundamental limits of what's actually possible versus what makes for compelling science fiction. So watch this video till the end and subscribe to the channel. Let's start. When astronomers tell us that Alpha Centauri is only 4.37 light-years away, it sounds almost achievable. In the grand cosmic scale, where galaxies are millions or billions of light-years apart, 4.37 light-years seems like practically next door. But this psychological framing is dangerous because it masks the absolutely staggering reality of what this distance actually means. Let's break down what 4.37 light-years actually represents. A light-year is the distance that light travels in 1 year, moving at approximately 299,792 kilometers per second. Fast enough to circle Earth's equator more than 7 times in a single second. In 1 year, traveling at this incomprehensible velocity, light covers about 9.46 trillion kilometers. Multiply that by 4.37, and you get approximately 41.3 trillion kilometers to Alpha Centauri. To put this in perspective, if you could drive a car at highway speed, 100 kilometers per hour, continuously without stopping, it would take you about 47 million years to reach Alpha Centauri. The human brain simply isn't equipped to truly comprehend distances on this scale. And this deceptive closeness creates a dangerous illusion that interstellar travel is merely a matter of building bigger rockets, when in reality, the distance to Alpha Centauri exists in an entirely different category of remoteness, one that may be permanently beyond the reach of physical travel. To understand why reaching Alpha Centauri is impossible with anything resembling current technology, we need to confront the speed problem head-on. This isn't about lacking powerful enough engines or efficient enough fuel. It's about the sheer magnitude of the velocity required and how pathetically slow even our fastest spacecraft are in comparison. Let's start with Voyager 1, humanity's most distant artificial object and our fastest spacecraft relative to the Sun. Launched in 1977, Voyager 1 was flung outward on a trajectory that used the gravity of Jupiter and Saturn to accelerate it to extraordinary speeds. After these gravitational assists, Voyager 1 is traveling at approximately 17 kilometers per second relative to the Sun, or about 61,200 kilometers per hour. This is astonishingly fast by any terrestrial standard. It's roughly 50 times the speed of a rifle bullet, and more than 600 times highway driving speed. Voyager 1 could travel from New York to Los Angeles in about 4 minutes. It reaches the distance to the moon in less than 6 hours, a journey that took the Apollo astronauts 3 days. By every measure of human experience, Voyager 1 is screaming through space at an incomprehensible velocity. And yet at this speed, Voyager 1 would take approximately 75,000 years to reach Alpha Centauri, if it were headed in that direction, which it isn't. Think about what that number means. 75,000 years ago, modern humans were just beginning to migrate out of Africa. The last ice age was underway. Neanderthals still walked the earth. The oldest known cave paintings wouldn't be created for another 30,000 years. All of recorded human history, from the first cities of Sumer through ancient Egypt, Greece, and Rome, through the Middle Ages and Renaissance, through the Industrial Revolution and into the modern era, represents only about 5,000 years, or roughly 7% of the time it would take Voyager to reach Alpha Centauri. In the time it would take that spacecraft to complete its journey, human civilization could rise and fall a dozen times over. But Voyager 1 represents our best current achievement after over 60 decades of space exploration. the spacecraft benefited from the most favorable planetary alignment possible for gravitational assists, a configuration that only occurs once every 176 years. It carries no crew, no life support systems, no return fuel. It's essentially an instrumentation package flying through space, never to return. And still, despite every advantage, despite being specifically designed and positioned to achieve maximum velocity, it crawls across interstellar distances at a pace that makes glaciers look swift. To put this in even starker perspective, Voyager 1 travels about 520 million kilometers per year. That sounds impressive until you realize that Alpha Centauri is approximately 41.3 trillion kilometers away. The spacecraft covers roughly 0.0000126% of that distance annually. At this rate, by the time Voyager 1 hypothetically reaches the distance to Alpha Centauri, our sun will have evolved significantly, potentially even beginning its expansion into a red giant phase that will eventually consume Earth itself. The mission would outlast not just civilizations, but potentially the very planet that launched it. Now consider what speeds we would actually need to make interstellar travel remotely practical. If we wanted to reach Alpha Centauri within a human lifetime, say 50 years, we would need to travel at approximately 26,230 kilometers per second, or about 8.75% of light speed. That's over 1,500 times faster than Voyager 1. If we were willing to accept a one-way mission where only the children or grandchildren of the original crew would arrive, making it a 150-year journey, we'd still need to travel at about 8,743 kilometers per second, still more than 500 times our fastest spacecraft. Even a 500-year journey, spanning roughly 20 generations, would require speeds of about 1,750 kilometers per second, or more than 100 times Voyager's velocity. These aren't small incremental improvements we're talking about. When engineers work on improving rocket efficiency or spacecraft design, they're typically looking for improvements of 5%, 10%, maybe 20% if they achieve a genuine breakthrough. But interstellar travel doesn't require incremental improvements. It requires improvements measured in orders of magnitude, in factors of hundreds or thousands. This is the fundamental disconnect that makes interstellar travel not just difficult, but essentially impossible with any foreseeable technology. We're not talking about making our spacecraft a little bit faster or a little bit more efficient. We're talking about achieving speeds that are so far beyond our current capabilities that they might as well be magic.
The reason we can't simply build bigger rockets to achieve these necessary speeds lies in one of the most tyrannical equations in all of physics, the Tsiolkovsky rocket equation, named after the Russian scientist Konstantin Tsiolkovsky, who derived it in 1897. This deceptively simple mathematical formula reveals why rocket propulsion faces fundamental limits that no amount of engineering cleverness can overcome. The equation states that the change in velocity a rocket can achieve is equal to the exhaust velocity of its propellant multiplied by the natural logarithm of the ratio between its initial mass, with fuel, and its final mass, without fuel. What this means in practical terms is absolutely devastating for anyone dreaming of interstellar travel. Here's the vicious cycle that dooms conventional rocketry. Every kilogram of payload you want to send to Alpha Centauri requires a certain amount of fuel to accelerate it. But that fuel has mass too, which means you need additional fuel to accelerate the fuel itself. And that additional fuel also has mass, requiring even more fuel to accelerate it. This compounds exponentially in a nightmarish spiral where the fuel requirements grow not linearly, but logarithmically with the desired velocity change. For modest speed increases, this isn't catastrophic, it's manageable. But for the enormous velocities needed for interstellar travel, the fuel requirements become absurd beyond comprehension. Let's work through a concrete example using chemical rockets, the technology that has powered every spacecraft humanity has ever launched. The best chemical rocket fuels, like liquid hydrogen and liquid oxygen used in rockets such as the Space Shuttle's main engines, have an exhaust velocity of about 4.4 kilometers per second. This is close to the theoretical maximum for chemical combustion. You simply cannot get much more energetic chemical reactions than burning hydrogen and oxygen. Now, if we wanted to accelerate even a tiny spacecraft, let's say just 1,000 kilograms, about the mass of a small car, to just 1% of the speed of light, which would still take 437 years to reach Alpha Centauri, we would need approximately 10 to the 38th kilograms of fuel. That's a 1 followed by 38 zeros. To put this in perspective, the entire mass of planet Earth is only about 6 times 10 to the 24th kilograms. We would need fuel equivalent to 170 trillion Earths. The entire observable universe doesn't contain enough matter to fuel this single spacecraft using chemical rockets. Even if we accepted far more modest goals, the numbers remain impossible. Suppose we wanted to reach just 0.1% of light speed, meaning the journey would take 4,370 years, still multiple times longer than all of recorded human history. Even at this glacial pace by interstellar standards, the fuel requirements for our 1,000-kilogram payload would be roughly 10 to the 8th kilograms, or 100,000 tons of fuel for every ton of payload. The International Space Station, one of the largest objects ever launched into space and assembled over dozens of missions, has a mass of about 420,000 kilograms. We'd need to launch something equivalent to the entire ISS just to carry the fuel for our small probe. And that's before accounting for the massive fuel tanks, engines, and support structure needed to contain and burn all that propellant. The logarithmic nature of the rocket equation means that the relationship between velocity and fuel is brutally nonlinear. Double your desired speed, and you don't need twice as much fuel, you need exponentially more fuel. This is why chemical rockets can barely escape Earth's gravity well and can achieve useful speeds for traveling within our solar system, but are utterly useless for interstellar journeys. They're fundamentally the wrong tool for the job, like trying to cross an ocean in a car or reach orbit by climbing a ladder. It's not that the car isn't fast enough or the ladder isn't tall enough. It's that these tools are categorically incapable of accomplishing the task regardless of how much you improve them. The tyranny of the rocket equation gets even worse when you consider that we've been talking only about acceleration. If you want to actually stop at Alpha Centauri rather than shooting past it at enormous velocity, which would be necessary for any useful mission, you need to carry fuel for deceleration too. This roughly doubles your fuel requirements, which, because of the exponential nature of the equation, actually squares the fuel ratio. Now you're not looking at impossible fuel requirements, you're looking at impossible squared fuel requirements. The spacecraft would need to carry enough fuel to decelerate its enormous fuel tanks along with everything else, creating yet another level of exponential growth in the mass ratio. Some might argue that we could refuel along the way, perhaps by stopping at intermediate destinations or mining comets for propellant. But this fundamentally misunderstands the problem. First, there are no convenient stopping points between here and Alpha Centauri. Interstellar space is almost perfectly empty. Second, even if there were, slowing down to stop at them would require carrying deceleration fuel, which takes us right back to the exponential fuel problem. And third, the process of mining, refining, and producing rocket fuel would require massive industrial equipment, which would need to be carried along, making the payload vastly heavier and requiring exponentially more fuel to move. Every solution to the rocket equation's tyranny just creates new problems that amplify the original issue. The rocket equation also reveals why staging, the practice of dropping empty fuel tanks as they're depleted, while helpful for getting off Earth, doesn't solve the interstellar problem. Staging works because you're shedding dead weight, improving your mass ratio as you go. But for the velocities needed to reach another star system, you would need so many stages that the staging hardware itself would constitute most of your mass. You'd end up with a spacecraft that's 99.99999% staging mechanisms and fuel tanks with an infinitesimally small payload. Beyond the tyranny of the rocket equation lies an even more fundamental barrier: the sheer energy requirements for accelerating anything to relativistic speeds. Even if we could somehow solve the fuel mass problem through some miraculous propulsion technology, we would still face the immutable laws of physics regarding kinetic energy. The numbers here are so staggering that they expose interstellar travel as not just an engineering challenge, but an energy crisis of cosmic proportions. Let's calculate the kinetic energy required to accelerate a small probe, say 1,000 kilograms, roughly the mass of the Voyager spacecraft, to 10% of the speed of light. At these velocities, we need to use the relativistic kinetic energy equation because Newtonian physics starts to break down, though at 10% light speed, the relativistic effects are still relatively small. The kinetic energy equals approximately 4.5 times 10 to the 17 joules. That's 450 petajoules, or 450,000 trillion joules of energy. To put this in context, the atomic bomb dropped on Hiroshima released about 63 terajoules of energy. Our small spacecraft would require the energy equivalent of roughly 7,000 Hiroshima bombs just to reach 10% of light speed. And that's assuming perfect conversion efficiency, which is physically impossible.
Now, let's compare this to humanity's total energy production. As of the early 2020s, human civilization consumes approximately 580 exajoules of energy per year from all sources combined: fossil fuels, nuclear power, renewables, everything. That's 5.8 times 10 to the 20th joules annually. Our 1,000 kilogram probe at 10% light speed requires 4.5 times 10 to the 17th joules, which represents about 0.078% of humanity's annual energy production. That might sound manageable until you consider what it actually means. We would need to dedicate roughly 1/3 of a day's worth of the entire planet's energy output. Every power plant, every solar panel, every wind turbine, every drop of oil burned to launching this single small probe. No lights, no heating, no industry, no transportation, no hospitals. Everything humanity produces energetically for 8 hours would need to go into accelerating one washing machine-sized spacecraft. But this dramatically understates the real problem because of efficiency losses. No energy conversion process is perfectly efficient. Rocket engines, even the most advanced ones, typically achieve efficiencies of 60 to 70% at best. More realistically, for the kinds of exotic propulsion systems we'd need for these speeds, we'd be lucky to achieve 30 to 40% efficiency when accounting for all energy conversion losses. This means we'd actually need to generate 2 to 3 times as much energy as the kinetic energy of the spacecraft, perhaps a full day of humanity's entire energy output for our tiny probe. And remember, this is just to accelerate it. If we want to decelerate at the destination, we need that much energy again, doubling our requirements to perhaps 2 full days of planetary energy output. Now consider that a 1,000 kilogram probe is essentially useless for any serious scientific mission, let alone a crewed expedition. It could carry a few instruments, perhaps a camera and some basic sensors, but that's about it. A meaningful robotic mission, something comparable to the Mars rovers that have given us such remarkable science, would need to be at least 10 times more massive to carry comprehensive instrumentation, communication equipment, power systems, and scientific instruments. That's 10 days of global energy output for acceleration alone, 20 days if we want to stop at the destination. A crewed mission, with life support, habitation modules, supplies, and the crew themselves, would easily mass 100,000 kilograms or more, probably much more. We're now talking about decades of humanity's total energy production for a single mission. The energy problem becomes even more insurmountable when we consider that this energy needs to be delivered to the spacecraft in a useful form. We can't just point all of Earth's power plants at a spacecraft and expect it to accelerate. The energy needs to be converted into kinetic energy of propellant, or electromagnetic radiation for a light sail, or antimatter fuel, or whatever exotic propulsion system we're imagining. Each conversion step loses efficiency. When you account for generating the energy, converting it to a usable form, storing it if necessary, and finally converting it to thrust, the total energy requirements could easily be 5 to 10 times the theoretical minimum. We're now talking about potentially weeks or months of planetary energy output for a small probe, years for a larger mission. Let's extend this to even more ambitious scenarios. Suppose we wanted to send a spacecraft at 20% of light speed, still taking over 20 years to reach Alpha Centauri, but at least within a human career span. Kinetic energy increases with the square of velocity, so doubling the speed quadruples the energy requirements. Our 1,000 kilogram probe would now need roughly 1.8 times 10 to the 18th joules, or about 3 days of global energy output just for the kinetic energy, probably a week or more accounting for inefficiencies. At 50% of light speed,
Making the journey less than 9 years, the relativistic effects become significant and the energy requirements skyrocket to about 1.5 times 10 to the 19th joules, roughly 26 days of planetary energy output for the kinetic energy alone, possibly 2 to 3 months accounting for real-world inefficiencies. Here's another way to visualize this energy problem. Humanity's total annual energy consumption is equivalent to burning about 14 billion tons of oil. To accelerate our small 1,000-kilogram probe to 10% light speed with realistic efficiency, we'd need the energy from burning roughly 40 million tons of oil, almost 3 supertankers full of petroleum, and that's using optimistic efficiency assumptions. For a crewed mission massing 100,000 kilograms, we'd need roughly 4 billion tons of oil equivalent, or about 30% of humanity's annual energy consumption. And oil is actually a terrible fuel for this purpose because of the rocket equation. This is just to illustrate the energy magnitude. The situation becomes truly hopeless when you consider the infrastructure required to generate and deliver this energy. You can't just build a giant power plant next to your launch pad. The energy needs to be converted into propulsion, which for chemical or even nuclear rockets means it's stored in the propellant. For a light sail, it means building enormous laser arrays. For antimatter propulsion, it means producing and storing antimatter. Each of these approaches requires not just the energy itself, but massive infrastructure to generate, convert, store, and deliver it. This infrastructure would cost trillions of dollars to build and would itself consume enormous amounts of energy in its construction and operation. Even if we somehow solve the energy problem, perhaps through fusion power or massive solar arrays, we would still face the brutal reality of the acceleration problem. Energy isn't useful unless you can convert it into thrust over time. And the timescales required to accelerate to interstellar velocities reveal yet another insurmountable barrier. This is where the fantasy of interstellar travel crashes against the hard limits of what propulsion systems can actually do in practice. Let's start with a basic principle. Acceleration equals force divided by mass, and changing your velocity requires sustained acceleration over time. For human comfort and survival, acceleration is typically limited to a few times Earth's gravity at most. Fighter pilots can withstand about 9 Gs for short periods with special suits, but sustained acceleration for a long journey would need to be far gentler, perhaps 1 G, the acceleration we experience standing on Earth's surface, which would feel like normal gravity. At a constant 1 G acceleration, reaching 10% of the speed of light would take approximately 35 days. That sounds manageable until you realize what it actually means. We would need to dedicate 35 days of continuous, uninterrupted thrust at full power. No propulsion system humanity has ever built can sustain thrust for 35 days straight. The most powerful rockets we've created, the Saturn V that sent astronauts to the moon or the space shuttle main engines, burn for minutes, not days. The first stage of the Saturn V burned for about 2.5 minutes. The space shuttle main engines ran for approximately 8.5 minutes to reach orbit. Even the most efficient chemical rocket engines ever designed can't burn continuously for days because they would overheat, their components would fail, and they would run out of propellant long before achieving the necessary velocity change. The engines on spacecraft like the Dawn mission, which used ion propulsion, one of our most advanced technologies, can run for years, but they produce thrust measured in tiny fractions of a newton, acceleration so minuscule that it would take centuries to reach even a small percentage of light speed. Let's examine ion drives more closely because they represent our current best technology for sustained thrust. The Dawn spacecraft's ion engine produced about 90 millinewtons of thrust, roughly the force you'd feel from holding a single piece of paper. For a spacecraft massing 1,000 kilograms, this produces an acceleration of 0.0009 meters per second squared, or about 0.0009 Gs. At this acceleration rate, reaching just 1% of light speed would take approximately 105 years of continuous thrusting. To reach our target of 10% light speed, you'd need over 1,000 years of continuous engine operation. And remember, this is just for a tiny 1,000-kilogram spacecraft. Scale up to something that could carry humans and supplies, and the acceleration becomes even more pathetic.
You might think the solution is simply to build more powerful ion engines or use multiple engines in parallel, but this runs directly into the mass problem again. More powerful engines are heavier, requiring more structure to support them, more power generation capacity to run them, and more propellant to feed them. The propellant for ion engines, typically xenon gas, also has mass that needs to be carried. And while ion drives are far more efficient than chemical rockets in terms of propellant usage, they still need substantial amounts for journeys of this magnitude. A mission lasting decades or centuries of continuous thrust would require massive propellant reserves. Consider a more powerful propulsion concept, nuclear thermal rockets, which use a nuclear reactor to superheat propellant before expelling it at a high velocity. These could theoretically produce much more thrust than ion drives, while still being more efficient than chemical rockets. An advanced nuclear thermal rocket might produce specific impulses around 900 seconds, compared to about 450 for the best chemical rockets and 3,000 to 10,000 for ion drives. With such a system providing reasonable thrust, say enough to accelerate at 0.1 g, you could reach 10% of light speed in about 350 days. That seems almost reasonable, until you consider that no nuclear reactor has ever been designed to operate at full power continuously for nearly a year in the harsh environment of space. Terrestrial nuclear reactors undergo regular maintenance and refueling cycles. The engineering challenges of building a reactor that could run flawlessly at maximum power output for a year straight with no possibility of repair or maintenance in a radiation-filled vacuum while undergoing constant acceleration are staggering. The thermal management alone would be nightmarish. Rocket engines generate enormous amounts of waste heat that must be radiated away into space. The space shuttle's main engines operated at combustion temperatures exceeding 3,300 degrees Celsius and required sophisticated cooling systems. For a nuclear thermal rocket running continuously for months, you need massive radiators to dissipate the waste heat from both the reactor and the rocket nozzle. These radiators would add significant mass to the spacecraft, reducing acceleration and requiring even more propellant. And unlike on Earth, where you can use air or water for cooling, in space, the only way to shed heat is through thermal radiation, which is far less efficient and requires large surface areas. Let's consider an even more exotic propulsion system, nuclear pulse propulsion, like the famous Project Orion concept from the 1950s and 60s. This wild idea involved attaining nuclear bombs behind a spacecraft and riding the shock wave, using a massive shock absorber plate to convert the explosion's energy into thrust. The concept could theoretically produce enormous thrust and achieve high velocities, but the acceleration profile would be jerky, periods of intense acceleration with each detonation followed by coasting, making sustained, smooth acceleration impossible. More fundamentally, you need thousands or tens of thousands of nuclear devices to reach the velocities we're discussing. The mass of all those bombs, their storage mechanisms, and the deployment systems would be astronomical, and the environmental implications of launching a spacecraft carrying thousands of nuclear weapons are obviously prohibitive. The acceleration problem also interacts catastrophically with the energy problem we discussed earlier. To maintain 1 g of acceleration for 35 days requires not just the total energy to reach 10% light speed, but that energy delivered at a specific rate, as power, not just total energy. Power is energy per unit time, and the power requirements for rapid acceleration are immense. Accelerating our 1,000 kilogram probe at 1 g requires a continuous power output of about 300 megawatts, equivalent to a medium-sized power plant running continuously for over a month. Where does this power come from? Solar panels would be useless. They couldn't possibly generate enough power and would add too much mass. Nuclear reactors could work in theory, but we've never built a space-rated reactor capable of 300 megawatts of continuous output. The entire International Space Station generates less than 100 kilowatts from its solar arrays. We'd need 3,000 times more power for our tiny probe. If we somehow solve the propulsion problem and actually manage to accelerate a spacecraft to a meaningful fraction of light speed, we would immediately encounter one of the most insidious and unavoidable hazards of interstellar travel. The universe itself becomes a deadly radiation field. This isn't about cosmic rays or solar radiation, problems we already know how to handle for near-Earth missions. This is about the fundamental transformation that occurs when you move at relativistic speeds through space that appears empty but actually contains low-density matter and radiation. At these velocities, the benign becomes lethal, and there is no practical shielding solution.
Let's start with something that seems completely harmless: the cosmic microwave background. This is the leftover glow from the Big Bang, a faint microwave radiation that permeates all of space, with a temperature of about 2.7 Kelvin above absolute zero. On Earth, we can detect it with sensitive instruments, but it's utterly harmless, far too weak to cause any damage whatsoever. However, this changes drastically when you're moving at relativistic speeds due to a phenomenon called the relativistic Doppler effect. Just like a siren sounds higher pitched when an ambulance approaches you, electromagnetic radiation becomes blue-shifted to higher frequencies and energies when you're moving toward its source at high velocity. At 10% of the speed of light, the cosmic microwave background in front of your spacecraft would be blue-shifted from benign microwaves into infrared and visible light, increasing in energy by a factor determined by relativistic physics. More importantly, the radiation would become dramatically more intense from your frame of reference. At 50% of light speed, the CMB in your forward direction would be blue-shifted into ultraviolet and X-ray wavelengths. At 90% of light speed, it would become gamma radiation, the same type of radiation that kills cancer cells and can sterilize equipment. The spacecraft and any crew would be bombarded by what is essentially a continuous gamma ray blast from the universe's background radiation itself, something that is completely harmless to us on Earth but becomes lethal at high relativistic velocities. But the cosmic microwave background is actually the least of your radiation problems. Far more dangerous are the hydrogen atoms that drift through interstellar space. Space is often described as a perfect vacuum, but this is misleading. Interstellar space contains approximately 1 hydrogen atom per cubic centimeter on average, an incredibly low density but not zero. When you're moving at everyday speeds or even at the 17 kilometers per second that Voyager travels, these hydrogen atoms are irrelevant. They simply bounce off your spacecraft with negligible energy. But at relativistic speeds, these atoms become deadly projectiles.
Consider a spacecraft traveling at 10% of the speed of light, encountering a stationary hydrogen atom. From the spacecraft's reference frame, that hydrogen atom is approaching at 10% light speed, or about 30,000 kilometers per second. A hydrogen atom has a mass of approximately 1.67 times 10 to the minus 27 kilograms, almost nothing. But at this velocity, its kinetic energy is about 7.5 times 10 to the minus 14 joules. That might sound tiny, but remember that this is energy delivered to an atomic scale impact point. When you calculate the energy per unit mass, each hydrogen atom hits with the energy equivalent of its mass multiplied by about 10 to the 13 joules per kilogram. For comparison, TNT releases about 4.6 million joules per kilogram. These hydrogen atoms are hitting your spacecraft with energy concentrations millions of times more intense than high explosives. At 20% of light speed, the situation becomes 4 times worse due to the squared relationship between kinetic energy and velocity. Each hydrogen atom now carries 4 times the energy, hitting with a force that can displace atoms in your spacecraft's hull, creating radiation damage at the molecular level. The hydrogen atoms don't just bounce off, they penetrate into the material, breaking chemical bonds and creating cascades of secondary particles. This is essentially the same type of radiation damage that occurs in nuclear reactors, where high-energy particles damage the reactor vessel over time, making the metal brittle and eventually requiring replacement of components. Except in a spacecraft traveling at relativistic speeds, there is no possibility of replacement or repair. Let's calculate the actual flux of these particle impacts. At 10% of light speed, a spacecraft is covering 30,000 kilometers every second. With approximately 1 hydrogen atom per cubic centimeter of space, the front surface of the spacecraft encounters about 3 times 10 to the 14 hydrogen atoms per square meter per second. That's 300 trillion atoms hitting every square meter of the front hull every single second. Even though each atom is tiny, the cumulative effect is devastating. Over the course of a year, and remember, even at 10% light speed, the journey takes over 40 years, each square meter of the forward hull would be struck by approximately 10 to the 22 hydrogen atoms. This would thoroughly destroy any material we know how to make. The secondary radiation produced by these collisions makes the problem even worse. When a high-energy hydrogen atom strikes the hull material, let's say aluminum, a common spacecraft material, it doesn't just make a tiny hole. It creates a shower of secondary particles, X-rays from the deceleration of the charged particle,
neutrons knocked out of aluminum nuclei, gamma rays from nuclear excitations, and a cascade of lighter particles. These secondary particles then penetrate deeper into the spacecraft, irradiating interior components and any crew. It's like every square meter of your hull is constantly being bombarded by a particle accelerator beam. The radiation dose to the crew would accumulate to lethal levels within days or weeks, even with significant shielding. Speaking of shielding, you might think the solution is simply to add thick armor to the front of the spacecraft. But this creates multiple problems. First, the more shielding mass you add, the more your spacecraft weighs, the more energy you need to accelerate it, and the worse all our previous problems become. Second, and more fundamentally, thick shielding actually makes the secondary radiation problem worse, not better. When high-energy particles strike thick shielding, they create extensive particle showers, cascades of secondary particles that can be more dangerous than the original particle. This is the same reason that lead shielding, while excellent for stopping gamma rays at low energies, becomes less effective at very high energies, where pair production and other effects create secondary radiation. Some have proposed using magnetic fields to deflect charged particles, similar to how Earth's magnetic field protects us from solar wind. But the energies involved at relativistic speeds are far too high for practical magnetic shielding. To deflect a hydrogen atom moving at 10% of light speed would require magnetic fields of extraordinary strength, far beyond what we can generate with superconducting magnets or any other technology. The power requirements for maintaining such fields would be enormous. The equipment would be massive, and even then, it would only work for charged particles. Neutral atoms and photons would pass right through unaffected. While individual hydrogen atoms at relativistic speeds pose a serious radiation hazard, they're actually not the worst of what interstellar space has to offer. Far more catastrophic are the dust particles and microscopic debris that drift through the interstellar medium. These tiny grains, typically measuring just micrometers to millimeters across, are so small and sparse that we barely notice them from Earth. But at fractional light speeds, even a single grain becomes a kinetic energy weapon capable of catastrophic damage. This is where the dream of high-speed interstellar travel doesn't just become difficult, it actually becomes actively suicidal. The interstellar medium isn't completely empty. Besides the hydrogen atoms we discussed, space contains dust grains, composed of silicates, carbon compounds, and ice particles. These grains are incredibly sparse, perhaps one grain larger than a micrometer per several cubic kilometers of space. That sounds negligible until you consider the enormous volume of space a fast-moving spacecraft sweeps through and the devastating energy these particles carry at high velocities. A dust grain that would harmlessly bounce off your car's windshield on Earth becomes a hypervelocity impactor that makes bullets look gentle by comparison. Let's calculate the kinetic energy of a grain of sand, something utterly mundane and harmless in everyday life, hitting a spacecraft traveling at 10% of the speed of light. A typical grain of sand has a mass of about 1 milligram, or 1 × 10⁻⁶ kilograms. At 10% of light speed, which is 30,000 kilometers per second, the kinetic energy of this grain is approximately 450,000 joules. To put this in perspective, a rifle bullet from a high-powered hunting rifle has a kinetic energy of about 4,000 joules. Our harmless sand grain at relativistic speeds hits with more than 100 times the energy of a rifle bullet. A hand grenade releases about 400,000 joules of energy, roughly equivalent to our one single grain impact.
Now imagine this hand grenade equivalent of energy being delivered not across a radius of several meters as with an actual grenade, but concentrated into a point smaller than a millimeter across. The energy density is absolutely astronomical. The impact would instantly vaporize the sand grain and a substantial portion of the spacecraft hull at the impact point, creating a plasma fireball that expands explosively both forward and backward. The shock wave propagating through the hull material would create a crater many times larger than the original particle, potentially punching completely through thin sections of the spacecraft. Any electronics, structural members, or equipment in the vicinity would be destroyed instantly. At 20% of light speed, the situation becomes 4 times worse. Our sand grain now carries 1.8 million joules of energy, equivalent to about 4 hand grenades or nearly half a kilogram of TNT. At 50% of light speed, we're talking about 28 million joules per sand grain, equivalent to about 6.5 kilograms of TNT. A single grain of sand now hits with the explosive force of a small bomb. At these velocities, even microscopic dust particles become devastating. A particle just 10 micrometers across, smaller than a human cell, at 50% light speed carries kinetic energy comparable to a bullet. The spacecraft is essentially flying through a shooting gallery, where every microscopic speck of dust is a projectile. The frequency of these impacts depends on the density of dust in the interstellar medium and the cross-sectional area of your spacecraft. Estimates suggest that interstellar dust with masses greater than 1 microgram, smaller than our sand grain but still significant, might be encountered at a rate of 1 particle per several hundred cubic kilometers. A spacecraft with a frontal area of 100 square meters, traveling at 10% of light speed, sweeps through approximately 3 times 10 to the 11th cubic meters of space per second, or about 10 to the 19th cubic meters per year. Even with the extremely low density of interstellar dust, you might encounter dozens to hundreds of significant impacts per year of travel. Over a 40-year journey to Alpha Centauri, you're virtually guaranteed to take multiple hits from particles carrying explosive-level energies, and thousands or millions of hits from smaller particles that would still cause serious damage. The randomness of these impacts makes them particularly insidious. You can't predict when or where they'll strike. Unlike radiation, which is constant and can be planned for, dust impacts are statistical events. Your spacecraft might go years without a serious hit, then suddenly take a catastrophic impact that destroys a critical system. It's like traveling in a vehicle where, at any random moment, without warning, a grenade might explode against the hull. No mission planning can account for this level of unpredictability. You can't carry enough redundant systems to survive unlimited random explosive impacts to arbitrary locations on your spacecraft. Some have proposed solutions to the dust problem, but none are practical. One idea is to place a shield in front of the spacecraft, a sacrificial barrier that would absorb impacts before they reach the main vessel. This is called a Whipple shield in spacecraft design, and it works well for orbital velocities where micrometeorites travel at a few kilometers per second. But at relativistic speeds, the physics changes fundamentally. When a particle hits a shield at 10% of light speed, it doesn't just damage the shield, it creates a plasma explosion that generates a cone of secondary debris traveling at nearly the same velocity as the original particle. This debris cone then strikes the spacecraft behind the shield, potentially causing as much or more damage than the original impact would have. To be effective, the shield would need to be placed very far in front of the spacecraft, perhaps hundreds or thousands of kilometers ahead to allow the plasma and debris from impacts to disperse before reaching the main vessel. But now you need to maintain the separation while accelerating, decelerating, and maneuvering. The shield needs its own propulsion system, navigation, and control, effectively making it a separate spacecraft. The mass penalty becomes enormous, and you've now doubled your chances of a catastrophic impact, because both the shield and the main spacecraft can be hit. And if the shield takes damage, you have no way to repair it or replace it during the journey. Another proposed solution is to use powerful lasers or particle beams to vaporize incoming dust before it strikes the spacecraft. This sounds like science fiction, and it is, but let's examine why it's impossible. First, you'd need to detect the incoming particles at sufficient range to target and destroy them before impact. At 10% of light speed, you're covering 30,000 kilometers per second. To have even 1 second of warning, you'd need to detect micrometer-sized particles at 30,000 kilometers distance. Our best telescopes can't reliably detect objects this small at such distances, even when we know exactly where to look. Detecting them in real time across the entire frontal hemisphere of your spacecraft is fantasy. Even if you could detect them, you'd need to track thousands or millions of particles simultaneously and engage each with enough energy to vaporize it before impact. The power requirements would be staggering. You'd need weapons-grade lasers operating continuously, consuming enormous amounts of power that your spacecraft needs for propulsion and life support. And here's the fundamental problem. Vaporizing the particle doesn't eliminate the threat. The vaporized material is still traveling at the same velocity toward your spacecraft. You've just transformed one solid projectile into a cloud of plasma, which might actually be worse because it spreads out and can damage a larger area. You haven't solved the problem, you've just changed its form.
Even if we somehow built a spacecraft capable of surviving the journey to Alpha Centauri, we would face a challenge that no amount of engineering can overcome: the fundamental speed limit of information itself. Light and all electromagnetic radiation, including radio signals, travels at 299,792 kilometers per second, and nothing in the universe can go faster. This means that communication with any interstellar spacecraft is subject to delays that make real-time mission control completely impossible. The implications of this are far more profound than they might initially appear, fundamentally changing the nature of what an interstellar mission would entail. Consider a spacecraft that has somehow reached Alpha Centauri 4.37 light-years away. When Mission Control on Earth sends a radio signal to the spacecraft, that signal travels at the speed of light and takes 4.37 years to arrive. If the spacecraft responds immediately, its response takes another 4.37 years to get back to Earth. The round-trip communication time is 8.74 years, nearly 9 years between asking a question and receiving an answer. Think about what this means in practical terms. If engineers on Earth notice something concerning in the telemetry data and send the message asking the spacecraft to check a specific system, the crew or computer won't receive that message for over 4 years. By the time the response reaches Earth, nearly 9 years will have passed since the problem was first noticed. Whatever was going to happen will have long since happened.
This communication delay makes troubleshooting essentially impossible in the traditional sense. Every space mission humanity has ever conducted has relied heavily on ground support. When Apollo 13 suffered an oxygen tank explosion, Mission Control worked frantically with the crew to devise solutions, running simulations and calculations on the ground and relaying procedures to the astronauts. The entire crisis played out over a few days with continuous communication. When the Mars rovers encounter problems, engineers on Earth spend days or weeks analyzing data, testing solutions, and uploading new commands. Even with Mars's light delay of up to 22 minutes at its furthest, this allows for iterative problem solving. But with Alpha Centauri, if a critical system fails, the spacecraft is entirely on its own for years before Earth even learns about the problem, let alone can suggest a solution. The psychological implications for a crewed mission are staggering. Imagine being an astronaut on this journey, knowing that any message you send home, a birthday greeting to your child, news of a discovery, or a call for help during an emergency, won't be heard for over 4 years. By the time your family responds to your message, their response is already obsolete, addressing a you that existed nearly 9 years ago. Your children will have grown up in the time it takes for a single exchange of messages. Your parents might have aged significantly or passed away between your message and their response. Romantic relationships would be impossible to maintain across such delays. You're not just separated by distance, you're separated by time in a very real sense, living in different epochs with a nearly decade-long gap between each interaction. For mission planners, this communication delay means the spacecraft must be designed with a level of autonomy and redundancy far beyond anything we've ever attempted. Every conceivable failure mode must be anticipated and pre-programmed with automated responses, because waiting for Earth's guidance is not an option. The spacecraft's computer systems must be sophisticated enough to diagnose problems, implement repairs, and make critical decisions without human oversight. This is an extraordinary requirement when you consider that even our most advanced autonomous systems today still rely on human intervention for unexpected situations. Self-driving cars, despite years of development, still struggle with unusual scenarios and require human takeover. Now imagine that level of autonomy needed for a spacecraft facing the unknown challenges of interstellar space, where the environment is poorly understood and anything unexpected could be fatal. The autonomy requirement extends to navigation and course corrections. If the spacecraft discovers it's slightly off course, perhaps due to an undetected gravitational perturbation or a propulsion system anomaly, it cannot wait for Earth to calculate and upload a correction. By the time Earth receives the telemetry showing the error, analyzes it, calculates a solution, and sends it back, nearly 9 years will have passed, and the spacecraft will be millions of kilometers off target. The spacecraft must have its own sophisticated navigation systems, capable of determining its position relative to distant stars, calculating optimal correction maneuvers, and executing them autonomously.
This requires carrying detailed star charts, sophisticated sensors, and powerful computers, all adding mass and complexity. Scientific decisions must also be pre-programmed or left to autonomous systems. Suppose the spacecraft detects something unexpected, perhaps an anomalous reading that could indicate a new phenomenon, or could be an instrument malfunction. On a conventional mission, scientists on Earth would examine this data, debate its meaning, and decide whether to devote resources to investigating it further or attribute it to noise. With Alpha Centauri, the spacecraft's AI must make these judgment calls alone. Do you investigate this anomaly and potentially waste precious fuel and time? Or do you continue with the primary mission and possibly miss a groundbreaking discovery? These are decisions that require scientific intuition and expertise that we cannot fully encode into software. The communication delay also means that Earth-based mission control will be observing history, not current events. When controllers look at telemetry data from Alpha Centauri, they're seeing what was happening 4.37 years ago. The spacecraft might have already encountered a catastrophic failure and been destroyed, but mission control won't know for over 4 years. They'll continue analyzing old data, making plans, and sending commands to a spacecraft that no longer exists, living in a past that the spacecraft has long since moved beyond. This temporal disconnect is deeply unsettling and unprecedented in human experience. Every mission we've done before had communication delays measured in minutes or hours at most, long enough to be inconvenient, but short enough that the mission state remained essentially current. Consider the arrival phase at Alpha Centauri, arguably the most critical and dangerous part of the mission. The spacecraft must decelerate from its enormous velocity, navigate to the target planet, enter orbit, and begin its scientific mission, all while Earth watches telemetry from over 4 years in the past. If something goes wrong during orbital insertion, if the spacecraft comes in too steep and burns up in an atmosphere, or too shallow and bounces off into space, Earth won't know about the failure until more than 4 years after it's already happened. Mission control will be helpless observers, watching ancient history unfold, unable to intervene or assist. The crew, if there is one, will succeed or fail entirely on their own. Navigation across interstellar distances requires a level of precision that pushes the limits of what's physically possible to measure and control. When traveling to the Moon or Mars, small errors in trajectory can be corrected relatively easily because the distances involved are manageable and course corrections require modest amounts of fuel. But across light years, the mathematics of error propagation become absolutely unforgiving. A minuscule mistake at the beginning of the journey, an error that would be considered negligible for any Earth-based application, compounds over trillions of kilometers into missing your target by distances larger than our entire solar system.
Let's examine the geometry of this problem. Imagine launching a spacecraft toward Alpha Centauri, which is 41.3 trillion kilometers away. Suppose your initial trajectory has an angular error of just 0.001 degrees. 1/1000th of a degree, an error so small it's difficult to even visualize. This seems like extraordinary precision. After all, most protractors only measure to the nearest degree. But over the distance to Alpha Centauri, this tiny angular error translates to a lateral deviation of approximately 720 billion kilometers, roughly 5 times the distance from the Sun to Pluto. Your spacecraft would miss the entire Alpha Centauri system by a margin wider than our solar system. You wouldn't even pass through the outer reaches of their equivalent of the Oort cloud. You'd sail right past into the void beyond. To put this in perspective, achieving 0.001 degree accuracy means that if you were aiming at a target 1 meter wide from a distance of 57 kilometers, you'd need to hit it perfectly. That's like standing in downtown Manhattan and trying to hit a basketball in Brooklyn, with no room for error. Except our target isn't 1 meter wide. Alpha Centauri is a star system spanning billions of kilometers. But we're not shooting from 57 kilometers away. We're shooting from 41.3 trillion kilometers away. The proportional precision required is staggering. To reliably arrive within a reasonable distance of Alpha Centauri, say within a few billion kilometers to allow for final approach maneuvers, you'd need initial trajectory accuracy better than 0.0001 degrees, or about 0.36 arcseconds. This is approaching the limit of what we can measure with our best instruments.
The challenge compounds because determining your exact position and velocity in space is extraordinarily difficult. On Earth, we have GPS satellites, landmarks, and a fixed reference frame. In interstellar space, you have only the distant stars for reference, and measuring tiny changes in their positions to determine your spacecraft's location requires instruments of exceptional precision. Current spacecraft navigation relies on radial tracking from Earth. We send signals to the spacecraft and measure the time delay and Doppler shift of the return signal to determine distance and velocity. But this technique becomes problematic for interstellar missions. First, there's a communication delay we discussed. You're navigating based on where Earth thinks you were over 4 years ago. Second, the precision of these measurements degrades with distance. Small errors in timing or frequency measurement translate to large errors in position when multiplied across light years. Even if you achieve near-perfect initial accuracy, your trajectory won't remain perfect. Space isn't actually empty. We've discussed the hydrogen atoms and dust, and each particle you hit imparts a tiny momentum change to your spacecraft. These are utterly negligible for short trips, but over decades or centuries of travel, millions of tiny impacts will gradually alter your course. The solar wind from our sun affects your trajectory for years after launch. As you pass through interstellar space, you'll encounter variations in particle density, magnetic fields, and potentially gravitational perturbations from objects we haven't detected, brown dwarfs, rogue planets, or concentrations of dark matter. Each of these influences nudges your spacecraft slightly off course, and over light years, slight nudges become catastrophic deviations. This is where course corrections become essential. But here we encounter yet another impossible problem. Course corrections require fuel. You need to fire thrusters to change your velocity vector. But we've already established that getting to high speeds requires enormous energy, and carrying fuel faces the tyranny of the rocket equation. Now you need to carry additional fuel reserves specifically for navigation corrections, and this fuel must last for the entire journey. Remember, at 10% light speed, the journey takes over 40 years. At more realistic speeds our current technology might achieve, we're talking centuries. Your fuel reserves for course corrections must remain usable, not frozen, not degraded, not leaked, for time periods longer than human institutions have existed. The timing of course corrections presents another dilemma. Ideally, you want to make corrections early in the journey because small adjustments made early require less fuel than large corrections made later. It's easier to change your angle slightly when you're closer to your starting point. But making corrections early means you're relying on navigation measurements taken at shorter distances, when the angular precision toward your target is worst. It's like trying to aim at a distant mountain from just a few kilometers away. Small uncertainties in angle matter much more. As you get farther from Earth and closer to your destination, your measurements of the target's position become more precise, but now you've traveled farther off course and corrections become more expensive in terms of fuel. Consider the mathematics of a mid-course correction. Suppose halfway to Alpha Centauri, about 20.6 trillion kilometers from Earth, your navigation systems determine you're off course by 100 billion kilometers. You need to change your velocity vector to redirect toward the target. At 10% of light speed, you're traveling at 30,000 kilometers per second. The velocity change required depends on the geometry, but even a relatively modest correction to adjust your path by billions of kilometers while traveling at these speeds might require a delta V of hundreds of kilometers per second. Remember from our discussion of the rocket equation that each kilometer per second of velocity change requires exponentially more fuel. You need to carry a substantial fraction of your spacecraft's mass as reserve fuel just for this one correction. And you might need multiple corrections throughout the journey. The situation becomes even more complex when you're traveling at high relativistic speeds, where time dilation becomes significant. From Earth's perspective, your spacecraft is taking 43 years to reach Alpha Centauri at 10% light speed. But due to time dilation, clocks on the spacecraft run slightly slower, about 0.5% slower at this speed. This sounds negligible until you remember that navigation requires extraordinarily precise timing. Your onboard clocks are running at a different rate than Earth clocks, and this must be accounted for in all navigation calculations. GPS satellites orbiting Earth experience time dilation effects of only a few microseconds per day, but this is enough to require constant correction. Without adjusting for relativity, GPS would accumulate positioning errors of kilometers per day.
Now imagine these effects playing out over decades of interstellar flight, with time dilation factors that, at higher speeds, become substantial.
Beyond all the technical challenges lies a biological reality that no amount of engineering can overcome. Human beings have finite lifespans, and interstellar journeys take longer than those lifespans in any realistic scenario. Even at 10% of the speed of light, a velocity we've already established is impossibly difficult to achieve, the one-way journey to Alpha Centauri takes 43 years. This isn't just a technical specification, it's a fundamental constraint that transforms the entire nature of what an interstellar mission would mean for the humans aboard. We're not talking about exploration in any traditional sense. We're talking about permanent exile, about people volunteering to spend their entire adult lives in transit, with no possibility of return and uncertain prospects of even reaching their destination alive. Consider what 43 years means in human terms. If you selected crew members at age 30, young enough to be physically fit and adaptable, old enough to have extensive training and maturity, they would be 73 years old upon arrival at Alpha Centauri. That's assuming they survived the journey, which is far from guaranteed given the radiation, the isolation, and the inevitable equipment failures over such a time span. These crew members would have spent their entire adult lives, from young adulthood through middle age and into old age, confined within a spacecraft. They would have no careers except this mission, no life except what exists within the metal walls of their vessel. Every birthday, every holiday, every significant life event would occur in the same artificial environment, millions of kilometers from any other human being who isn't part of their small crew. The return journey, if one were even planned, would take another 43 years. A crew member who left Earth at age 30 would be 116 years old upon returning home, far beyond current human life expectancy. In reality, a return journey is functionally impossible. The spacecraft would need to carry enough fuel to decelerate at Alpha Centauri, conduct its mission, then accelerate back toward Earth, and decelerate again upon arrival. We've already established that carrying fuel for even one-way acceleration is barely conceivable. Carrying fuel for the return journey multiplies the mass requirements to absurd levels. Any realistic interstellar mission would be one-way only. Crew members would be saying goodbye to Earth forever, knowing with absolute certainty that they would never see their home planet again, never breathe unrecycled air, never feel natural gravity, never see anyone they left behind. This creates profound implications for crew selection. Who volunteers for such a mission? It would attract a very specific type of person, perhaps those with nothing left on Earth, those fleeing from rather than traveling towards something, or those with such extreme dedication to exploration that they're willing to sacrifice everything. But these aren't necessarily the psychological profiles you want for a multi-decade mission requiring stability, cooperation, and mental resilience. The selection process would need to identify people willing to give up everything, family, friends, careers, any possibility of a normal human life, while simultaneously ensuring they're mentally stable enough to handle decades of confinement. These requirements might be mutually exclusive. The kind of person healthy enough to endure the journey might not be the kind of person willing to volunteer for it. The psychological challenges of such a journey exceed anything humanity has experienced. Our longest continuous space missions have been about a year on the International Space Station, and even these relatively short missions produce psychological strain, interpersonal conflicts, and a profound desire to return to Earth. Astronauts on the ISS can see Earth out their windows. They're never more than 400 kilometers from home, and they know their mission has a definite end date. They can communicate with loved ones in real time. If there's an emergency, they can potentially return to Earth within hours. An interstellar crew has none of these comforts. Earth becomes an increasingly distant point of light, eventually indistinguishable from other stars. Communication delays stretch to years. There is no possibility of abort, no emergency return option, no rescue if something catastrophically goes wrong. You are committed utterly and irrevocably to completing the journey or dying in the attempt. The social dynamics of a small crew confined together for 43 years would be extraordinarily complex. Research on isolated groups, Antarctic research stations, submarine crews, long-duration space missions shows that even carefully selected individuals develop conflicts, form cliques, and experience periods of depression and interpersonal tension.
These missions last months, occasionally a year or two. Now extend that to 43 years with the same small group of people with no possibility of leaving, no new faces, no change in scenery except through windows showing the unchanging void of space. Friendships would form and dissolve. Romantic relationships would develop, complicate, and potentially become sources of conflict in an environment there's no possibility of physical separation from an ex-partner. Personality conflicts that might be minor annoyances in a year-long mission become unbearable over decades. The question of children becomes unavoidable for such a long mission. If the crew consists of young, healthy adults, and if romantic relationships develop, which they almost certainly would over 43 years, then pregnancies are likely even with contraception. But raising children aboard an interstellar spacecraft presents ethical and practical nightmares. These children would be born into confinement, never experiencing Earth, never having a choice about their participation in the mission. They would grow up in microgravity or artificial gravity, which could affect their skeletal and muscular development in unknown ways. Their entire universe would be the interior of the spacecraft. What kind of psychological development occurs when a child never experiences nature, never meets anyone outside their tiny community, never has any conception of the variety and complexity of human civilization? And practically, children require resources, food, water, air, space, that must be accounted for in the mission planning, but you cannot predict exactly how many children might be born during a 43-year journey. This leads to the concept of generation ships, spacecraft designed explicitly for multi-generational journeys where the people who arrive are not the people who departed. If we accept that realistic interstellar travel might take centuries rather than decades, which is far more likely given the technological constraints we've discussed, then generation ships become the only option for crewed missions. The initial crew would have children, those children would have children, and perhaps several generations later, their descendants would reach Alpha Centauri. But this raises profound ethical questions. Is it morally acceptable to commit unborn generations to life aboard a spacecraft, denying them any choice in the matter? The original crew volunteers for the mission, but their children and grandchildren are born into it with no alternative. They're sentenced to life imprisonment for the crime of being born at the wrong time in the journey.
Creating a life support system that can sustain human life for the decades or centuries required for interstellar travel represents an engineering challenge that dwarfs anything humanity has accomplished. On the International Space Station, which represents our most advanced life support technology, astronauts depend on regular resupply missions from Earth, bringing fresh water, food, oxygen, spare parts, and other consumables every few months. Even with sophisticated recycling systems, the ISS cannot operate as a truly closed loop. It requires constant input from Earth to remain functional. For an interstellar mission, there are no resupply missions. Every molecule of water, every breath of oxygen, every calorie of food must either be carried from the beginning or recycled with near-perfect efficiency for the entire journey. The difference between 99% efficiency and 99.9% efficiency isn't marginal. It's the difference between survival and death. Let's start with the most basic requirement, breathing. An adult human consumes approximately 550 liters of oxygen per day and produces roughly the same volume of carbon dioxide. Over a 43-year journey to Alpha Centauri, a single person needs about 8.6 million liters of oxygen. That's about 12,000 kilograms of oxygen if stored as compressed gas. For a crew of this 10 people, you're looking at 120,000 kilograms of oxygen storage, and this doesn't account for losses, leaks, or any safety margins. Carrying this much oxygen is impractical, so you need regenerative systems that recycle the carbon dioxide back into oxygen. The ISS uses a combination of technologies, electrolysis to split water into hydrogen and oxygen, and the Sabatier reaction to convert carbon dioxide and hydrogen into water and methane. But these systems are not perfectly efficient. They lose small amounts of gases with every cycle, require regular maintenance, and depend on components that wear out. The inefficiency problem compounds catastrophically over long time frames. Suppose your oxygen recycling system is 99.5% efficient per cycle, an extraordinary achievement that would be considered excellent by current standards. This means that with each cycle, you lose 0.5% of your oxygen. Over 1 year with daily cycling, you've lost about 86% of your oxygen supply. You need reserve tanks to make up this loss. Over 43 years, even with this high efficiency, you'd need to carry enormous reserves.
And if your efficiency drops to 99%, still remarkable by today's standards, you lose essentially all your oxygen within a year. The mathematics of exponential decay are unforgiving. To maintain a stable atmosphere for decades, you need efficiency rates of 99.99% or higher, rates we've never achieved in practice and which may not be physically possible given unavoidable losses through leaks, chemical reactions with the spacecraft structure, and absorption into materials. Water presents a similar challenge, perhaps even more critical, because water is needed not just for drinking, but for hygiene, food preparation, oxygen production, and cooling systems. A human needs about 3 to 4 liters of drinking water per day, but total water usage for all purposes on the ISS is approximately 30 liters per person per day. Over 43 years, a single crew member needs nearly 470,000 liters of water. Water is heavy. 1 liter equals 1 kilogram. So for a 10-person crew, you're looking at 4.7 million kilograms of water if you carried it all from the start. This is obviously impossible. The ISS recycles water from urine, humidity in the air, and other sources, achieving recovery rates around 93 to 94%. This sounds impressive until you realize that losing 6 to 7% of your water with each recycling cycle means you'd exhaust your reserves in a matter of months. You need reserve rates exceeding 99% for a multi-decade mission, and achieving this is extraordinarily difficult. The challenge with water recycling isn't just the chemistry, it's also the biology. Human urine and wastewater contain not just water, but salts, organic compounds, urea, and other dissolved substances. Some of these can be filtered out, but filters clog over time and need replacement. Some require chemical processing that itself consumes resources. Some contaminants are difficult to remove completely, and as you recycle the same water thousands of times over decades, these contaminants can accumulate to toxic levels. You need filtration systems sophisticated enough to maintain water purity through 15,000 days of continuous operation, roughly 15,000 cycles if you're recycling daily. Every component in this system must be extraordinarily reliable, and you must carry spares for every component that might wear out, because a failure in your water recycling system means death within days. Food presents perhaps the most intractable problem. Unlike oxygen and water, which can theoretically be recycled through chemical and physical processes, food represents concentrated energy and complex organic molecules that are difficult to regenerate. The ISS receives all of its food from Earth, freeze-dried meals, packaged foods that last months or years. For a 43-year mission, you'd need to carry every calorie the crew will consume. An adult needs roughly 2,000 calories per day, or about 2 kilograms of food. Over 43 years, that's 31,000 kilograms of food per person, or 310,000 kilograms for a 10-person crew. 310 tons of food. And food doesn't last forever. Even the best preservation methods see food quality degrade over years. Frozen food can last decades if maintained at very low temperatures, but this requires substantial refrigeration equipment and constant power consumption. Freeze-dried food might last years, but not decades without degradation in nutritional value and edibility. The only realistic solution for food on timescales of decades is to grow it aboard the spacecraft, essentially creating a miniature agricultural ecosystem. But growing food in space is enormously challenging and has never been demonstrated at the scale required for full nutritional self-sufficiency. Plants need light, water, nutrients, and carbon dioxide. The light must be provided artificially using electricity. Natural sunlight diminishes rapidly as you move away from the sun and becomes negligible in interstellar space. A small garden on the ISS uses hundreds of watts of power. Scaling this up to feed an entire crew requires kilowatts of continuous power. And remember, every watt of power generation requires equipment with mass. The plants also need growing medium, which has mass, and nutrients, which must be supplied. Some nutrients can be recycled from human waste, but others need to be carried as reserves because biological systems always lose small amounts of materials. Nutrients that get incorporated into structures and can't be recovered, or that are lost through inefficient recycling.
Creating a truly closed ecological system is something we've never successfully done, even in controlled experiments on Earth. Biosphere 2, a 3.14-acre facility in Arizona designed to be a sealed ecosystem, failed to maintain atmospheric balance and required external intervention during its experiments in the 1990s. The facility's oxygen levels dropped and carbon dioxide levels rose to dangerous levels despite having vastly more biological mass and diversity than any spacecraft could carry. Plants,
soil bacteria, and the human occupants consumed oxygen faster than plants could produce it, and chemical reactions with the facility's concrete absorbed oxygen as well. If we can't maintain a closed ecosystem in a large facility on Earth with abundant sunlight and the ability to intervene when things go wrong, how can we expect to do it in a small spacecraft in interstellar space for decades without any possibility of external help? When confronted with the fundamental limitations of chemical rockets, many space enthusiasts point to nuclear propulsion as the solution that will finally make interstellar travel possible. Nuclear reactions release millions of times more energy per kilogram than chemical reactions, suggesting they could provide the enormous energy densities needed for high-velocity spaceflight. Indeed, nuclear propulsion concepts have been studied seriously since the 1950s and represent a genuine improvement over chemical rockets. But calling nuclear propulsion a solution to interstellar travel is like calling a sports car a solution to driving to the moon. Yes, it's faster than walking, but it's still not remotely adequate for the task at hand. Even the most optimistic nuclear propulsion concepts can achieve only a few % of light speed at best, and the practical and technical barriers to implementing them are staggering. Nuclear thermal rockets represent the most straightforward nuclear propulsion concept. Instead of burning chemical fuel, you use a nuclear reactor to heat propellant, typically hydrogen, to extremely high temperatures, then expel it through a nozzle to generate thrust. The advantage is that you can heat hydrogen to temperatures of 2500 to 3000 Kelvin or higher, well beyond what chemical combustion can achieve, giving you exhaust velocities around 9 kilometers per second compared to about 4.4 kilometers per second for the best chemical rockets. This roughly doubles your specific impulse, meaning you need less propellant for the same velocity change. Nuclear thermal rockets were seriously developed during Project Rover and NERVA in the 1960s and early 1970s. Prototype engines were built and tested, demonstrating that the concept works. But even with this improvement, the rocket equation still dominates. Doubling your exhaust velocity doesn't come close to solving the exponential fuel requirements for relativistic speeds. Let's calculate what a nuclear thermal rocket could actually achieve for an interstellar mission. With an exhaust velocity of 9 kilometers per second and using the Tsiolkovsky rocket equation, reaching just 1% of light speed, 3,000 kilometers per second, would require a mass ratio of about e to the 333, or roughly 10 to the 144. That's a 1 followed by 144 zeros. This is not just impractical, it's physically meaningless. There isn't that much mass in the observable universe. Even reaching a 1/10 of 1% of light speed, making the journey to Alpha Centauri take 4,370 years, would require a mass ratio of about 10 to the 14, or 100 trillion tons of propellant for every ton of payload. Nuclear thermal rockets are better than chemical rockets, but they're still hopelessly inadequate for interstellar travel. The fundamental problem is that they still work by throwing mass out the back, and the rocket equation remains tyrannical regardless of how hot you make your propellant. Nuclear pulse propulsion, exemplified by Project Orion, designed in the late 1950s, takes a radically different approach. Instead of using a reactor to heat propellant continuously, you detonate bombs behind your spacecraft and ride the shockwave. Each bomb provides an enormous impulse, a sudden kick of acceleration. By detonating bombs in rapid succession, perhaps one every few seconds, you could theoretically accelerate to very high velocities. The Orion concept envisioned a massive pusher plate on the back of the spacecraft, attached through shock absorbers that would smooth out the impulses into something humans could survive. Studies suggested that an Orion-type spacecraft could achieve exhaust velocities equivalent to thousands of kilometers per second, potentially reaching 3 to 5% of light speed given enough bombs and a large enough spacecraft. This would reduce the journey to Alpha Centauri to perhaps a century, still multiple human lifespans, but at least within the realm where generation ships become conceivable.
But nuclear pulse propulsion faces obstacles that have kept it purely theoretical for over 60 years. First, there's the environmental catastrophe of launching such a vehicle from Earth. The original Orion concept required detonating nuclear weapons in Earth's atmosphere or near Earth space during the acceleration phase. Each detonation would produce radioactive fallout and electromagnetic pulses. Launching a spacecraft that might require hundreds or thousands of nuclear detonations to reach its cruising velocity would spread radioactive contamination across a huge area and expose populations to elevated radiation levels. The Partial Nuclear Test Ban Treaty of 1963 explicitly prohibits nuclear weapons testing in the atmosphere, outer space, and underwater, effectively making atmospheric Orion launches illegal under international law. You could potentially assemble the spacecraft in space and begin detonations only after leaving Earth's vicinity, but this requires first launching thousands of nuclear devices into orbit using conventional rockets, a logistical nightmare.
The technical challenges are equally daunting. The pusher plate that absorbs the nuclear explosions must withstand repeated plasma impacts at temperatures of millions of degrees. While studies suggested that appropriate materials could survive, perhaps thick steel or carbon composite plates, there's enormous uncertainty because we've never actually tested this. The shock absorbers must function perfectly across thousands of detonation cycles, gradually degrading but never failing catastrophically, because a single failure could destroy the spacecraft. The nuclear devices themselves must be reliable. If even 1% of your bombs are duds or detonate improperly, the resulting asymmetric thrust could send your spacecraft tumbling or push it off course. And you need to carry all these bombs with you from the start, meaning your spacecraft's mass is dominated by nuclear weapons with all the safety, security, and handling challenges that implies. Even if we solved all these problems, nuclear pulse propulsion still only gets you to a few percent of light speed. The journey to Alpha Centauri would still take a century or more, far longer than a human lifespan. And you face all the other problems we've discussed: radiation damage from interstellar hydrogen, dust particle impacts, communication delays, navigation precision, and life support for multiple generations. Nuclear pulse propulsion makes the speed problem somewhat less impossible, but doesn't come close to solving it, while introducing a whole new category of environmental and safety problems that may be completely insurmountable. There are more exotic nuclear concepts, like nuclear electric propulsion, where a reactor generates electricity to power ion drives or other electric propulsion systems. The advantage is very high specific impulse, exhaust velocities of tens of kilometers per second, but the thrust is pathetically weak. We discussed earlier how ion drives can run for years but produce accelerations measured in millionths of a g. Adding a nuclear reactor to power them doesn't change this fundamental limitation. You get excellent fuel efficiency but glacial acceleration, and the mass of the reactor and its cooling systems eat into your payload capacity. For interstellar missions, you'd still need centuries to reach cruising velocity, and centuries more to decelerate. The journey time becomes so long that all the life support and reliability problems become completely unmanageable. When nuclear propulsion proves inadequate, the next proposed solution is always antimatter, the ultimate fuel that physics allows. When matter and antimatter meet, they annihilate completely, converting 100% of their combined mass directly into energy, according to Einstein's famous equation E equals mc squared. No other reaction comes close to this efficiency. Chemical reactions convert a tiny fraction of mass into energy through molecular bonds. Nuclear fission and fusion convert less than 1% of mass to energy. But matter-antimatter annihilation converts everything. The entire rest mass becomes pure energy. This makes antimatter the most energy-dense fuel theoretically possible, offering exhaust velocities approaching the speed of light itself. If you had enough antimatter, you could theoretically accelerate a spacecraft to significant fractions of light speed. The problem is that "if you had enough antimatter" is one of the biggest ifs in all of physics.
Antimatter doesn't exist naturally in any significant quantities in our region of the universe. When the universe formed, matter and antimatter should have been created in equal amounts, but for reasons still not fully understood, matter dominated and antimatter essentially disappeared. Today, tiny amounts of antimatter are created by high-energy cosmic ray collisions with Earth's atmosphere, but these amounts are infinitesimally small and immediately annihilate when they touch normal matter. If we want antimatter for fuel, we must manufacture it ourselves. And here's where the dream crashes against economic reality so hard that it's almost comical. Current antimatter production at facilities like CERN creates approximately 1 to 10 nanograms per year. That's billionths of a gram. At these production rates, it would take approximately 1 million years to produce a single gram of antimatter. The cost is even more absurd than the production rate. Estimates for the current cost of producing antimatter range from $25 trillion to $100 trillion per gram, and these aren't inflated worst-case estimates. They reflect the actual energy and infrastructure costs of current production methods. To understand why antimatter is so expensive, you need to understand how it's made. Antimatter is created by smashing high-energy particles into targets, occasionally producing matter-antimatter pairs. At CERN, protons are accelerated to enormous energies and crashed into targets, producing showers of particles, including antiprotons. These antiprotons are then captured using powerful magnetic fields, slowed down, and stored in electromagnetic traps, where they float in vacuum, never touching the walls, because any contact with normal matter causes instant annihilation. Every step of this process is staggeringly inefficient. The particle accelerators require enormous amounts of electricity. CERN's Large Hadron Collider uses about 200 megawatts when running, roughly the power consumption of a small city. This power accelerates trillions of protons, most of which never produce antimatter at all. Of the particle collisions that do produce antiprotons, only a tiny fraction of those antiprotons can actually be captured and stored. The rest annihilate immediately or escape the magnetic traps. For every unit of energy contained in the antimatter produced, you've spent billions or trillions of units of energy creating it. This isn't a problem we can engineer away. It's fundamental to the physics of how antimatter must be created using matter-based equipment. Now let's calculate how much antimatter an interstellar mission would actually need. Remember our 1,000 kilogram probe that we wanted to accelerate to 10% of light speed, requiring about 4.5 times 10 to the 17th joules of kinetic energy? If we could use antimatter with perfect efficiency, we'd need about 2.5 kilograms of antimatter matter fuel, roughly 1.25 kilograms of antimatter annihilating with 1.25 kilograms of matter. At current production rates of 10 nanograms per year, producing 1.25 kilograms would take 125 billion years, nearly 10 times the current age of the universe. At current costs of conservatively $25 trillion per gram, 1,250 grams would cost about $31 quadrillion, more than 300 times the entire gross domestic product of planet Earth. And this is for a tiny probe. A crewed mission massing 100,000 kilograms would need proportionally more antimatter, pushing costs into the realm of numbers that cease to have economic meaning.
Even if we could somehow scale up production dramatically, we face fundamental physical barriers. The inefficiency of antimatter production isn't just an engineering challenge, it's rooted in the basic physics of particle creation. When you create an antiproton in a collision, you must also create a proton due to conservation laws. You're always making equal amounts of matter and antimatter, and only the antimatter is useful as fuel while the matter is just waste. The energy threshold for creating proton-antiproton pairs is substantial, and you lose most of your input energy to other particles and processes. Even with perfect engineering and optimization, the best theoretical efficiency for antimatter production is probably around 0.01%. You need to put in 10,000 units of energy to get 1 unit of energy stored in antimatter.
This means that antimatter is fundamentally a way to store energy, not generate it. You're converting electrical energy into matter-antimatter pairs, storing the antimatter, and then later converting it back to energy. It's a battery, not a power source, and it's the most inefficient battery imaginable by factors of thousands. Storage presents yet another impossible challenge. Antimatter must never touch normal matter, or it annihilates instantly. Current storage uses electromagnetic traps, essentially magnetic bottles that suspend charged antiparticles in vacuum. These traps require continuous power to maintain the magnetic fields. If the power fails even briefly, the antimatter drifts into the trap walls and annihilates. For a spacecraft, you'd need antimatter storage that's absolutely fail-safe for decades, never losing power, never experiencing a magnetic field fluctuation, surviving the vibrations of launch and acceleration, and remaining stable through radiation impacts and micrometeorite hits. A single failure in your antimatter containment means your fuel, and probably your entire spacecraft, instantly vaporizes in a matter-antimatter explosion. We're talking about containing a substance more dangerous than anything else humans have ever handled, in quantities millions of times larger than we've ever produced for time periods thousands of times longer than we've ever stored it. The propulsion system itself faces severe challenges. You can't just burn antimatter in a rocket nozzle. When matter and antimatter annihilate, they produce gamma rays, charged particles called pions, and other high-energy radiation. Somehow you need to convert this radiation into directed thrust. Proposed designs involve magnetic nozzles that would use powerful magnetic fields to direct charged particles. But the gamma rays go straight through magnetic fields and escape in all directions, carrying away much of your energy with no thrust benefit. Realistic antimatter rockets might achieve efficiencies of 50 to 70% at best in converting annihilation energy to thrust. You've already lost 99.99% of your energy creating the antimatter. Now you're losing another 30 to 50% using it. The compounded inefficiency makes the entire concept economically absurd. In 2016, physicist Stephen Hawking and investor Yuri Milner announced Breakthrough Starshot, a concept that seemed to finally offer a realistic path to interstellar travel. The idea is elegant in its simplicity. Instead of carrying fuel, build an enormous array of lasers on Earth that beam energy to ultra-lightweight spacecraft equipped with reflective sails. The laser light pushes against the sail, accelerating the spacecraft to 20% of light speed in a matter of minutes. At this velocity, the journey to Alpha Centauri takes just over 20 years, within a human lifetime. The concept avoids the rocket equation entirely because the spacecraft carries no fuel. The energy source remains on Earth, beaming power across the void. Finally, it seems, we have a solution that might actually work. But as with every other proposal for interstellar travel, the details reveal why even this stripped-down concept faces barriers that may be insurmountable, and why it can only ever apply to the tiniest of probes, never to anything resembling a crewed mission. The Breakthrough Starshot concept envisions spacecraft called starships, tiny wafers massing about 1 gram, roughly the weight of a paperclip. These would carry a few miniaturized sensors, a camera, basic processing capability, and communication equipment, all mounted on a reflective sail about 4 meters across but massing less than a gram itself. The sail would be made of incredibly thin reflective material, perhaps just a few hundred atoms thick, stretched across an ultra-lightweight framework. An array of lasers on Earth with combined power output of 50 to 100 gigawatts would target this sail and fire for several minutes, accelerating the starship to 20% of light speed. This is the absolute minimum conceivable interstellar probe. Any smaller and you can't carry meaningful instruments or communications equipment. And yet, even this minimal concept requires technology that doesn't exist and faces challenges that may be insurmountable. Let's start with the laser array itself. A 100 gigawatt laser system would be one of the most powerful machines ever built, consuming as much electricity as a large country for the duration of the acceleration phase. For context, the entire installed electrical generating capacity of the United States is about 1,200 gigawatts, so we're talking about roughly 8% of America's total power generation capacity focused into a laser beam for several minutes. The infrastructure cost would be staggering. Estimates range from $5 to $10 billion just for the laser array. And this doesn't include the power generation facilities, cooling systems, targeting computers, and all the supporting infrastructure. You'd essentially be building a weapon capable of delivering enough energy to vaporize anything it touches, which raises obvious military and safety concerns. The array would need to be in a desert or remote location with extremely stable atmospheric conditions because even slight atmospheric turbulence causes beam distortion. The targeting precision required is almost incomprehensible. The laser beam must track a sail just 4 meters across as it accelerates away from Earth at increasing velocities. Within seconds, the sail is hundreds of kilometers away and moving at thousands of kilometers per second. Within minutes, it's millions of kilometers distant and approaching 20% of light speed, 60,000 kilometers per second. The laser beam must remain focused on this tiny, rapidly receding target with extraordinary precision. Any misalignment, and the laser energy misses the sail entirely, wasting gigawatts of power. The targeting system must compensate for the sail's acceleration, Earth's rotation, atmospheric refraction, and the fact that by the time your laser light reaches the sail's location, the sail has moved. You're essentially trying to hit a moving target the size of a small room from increasing distances measured in millions of kilometers while that target is accelerating away from you at relativistic speeds. This level of precision has never been demonstrated for any application. The sail itself must be a marvel of materials engineering that may not be physically possible. It needs to be reflective enough that 99.9% or more of the laser light bounces off rather than being absorbed. Any absorbed light becomes heat that could vaporize the ultra-thin material. It must be strong enough to withstand the acceleration forces without tearing, yet light enough that the entire sail masses less than a gram itself. It must remain perfectly flat and properly oriented during acceleration, despite being pushed by intense laser energy. Current proposals suggest materials like graphene or specially engineered metamaterials, but these remain largely theoretical for this application. Even tiny imperfections in the sail, a slightly less reflective spot, a microscopic hole, could cause uneven heating and acceleration, making the sail tumble or tear apart. And the sail must survive the acceleration phase and then continue functioning for 20 years of interstellar travel, protecting the delicate electronics behind it from dust impacts and radiation.
The acceleration forces involved are extreme. To reach 20% of light speed in a few minutes requires acceleration of roughly 60,000 Gs, 60,000 times Earth's gravity. This is why only the tiniest spacecraft can be considered. Electronics that must survive this acceleration need to be specially designed and tested, far beyond anything we've built before. Every component must be able to withstand forces that would instantly crush or shatter conventional spacecraft components. The mounting structures, the sail attachment points, every circuit board and sensor must be engineered to tolerances we've never achieved. And remember, if any component fails during acceleration, there's no abort option, no rescue. The spacecraft simply tumbles out of control into interstellar space as an expensive piece of debris. Even if everything works perfectly and your gram-scale probe successfully accelerates to 20% light speed, you still face all the challenges we've discussed. At this velocity, interstellar hydrogen atoms hit the spacecraft with tremendous energy, potentially damaging the delicate electronics. Dust particles would punch through the ultra-thin sail and destroy the craft instantly. The communication system must transmit data across 4.37 light-years using a transmitter powered by less than a gram of batteries or solar cells, probably insufficient to send more than a trickle of data. The entire mission becomes a high-risk gamble that your probe survives the journey and can transmit at least some useful information back before its power runs out or something destroys it. Now consider scaling this up to anything larger. Suppose you wanted to send a 100-gram probe instead of 1 gram, perhaps to carry more capable instruments, better communication equipment, and redundant systems. You'd need 100 times more laser power, 10 terawatts, which is nearly 10% of the world's total electricity generating capacity. The cost and infrastructure requirements scale proportionally. A 1 kilogram probe requires 100 terawatts. This is approaching the total power output of human civilization. A crewed spacecraft massing perhaps 100,000 kilograms would require 10 petawatts, 10 million billion watts, roughly 10,000 times humanity's total power generation capacity. Even if we could build such a laser array, firing it would require more energy than our entire civilization produces in a year, delivered in just a few minutes. The waste heat alone would be enough to melt the equipment. For over 70 years, fusion power has been promised as the solution to humanity's energy needs, and by extension, fusion rockets have been proposed as the key to interstellar travel. The appeal is obvious. Fusion reactions release millions of times more energy per kilogram than chemical reactions. The fuel, hydrogen isotopes, is relatively abundant, and unlike fission, fusion produces minimal long-lived radioactive waste. Fusion rockets theoretically could achieve exhaust velocities of thousands of kilometers per second, potentially enabling spacecraft to reach a few percent of light speed. Scientists and engineers have been working on fusion power since the 1950s, and we're constantly told that practical fusion is just a few decades away. Yet here we are, 7 decades later, and we still haven't achieved sustained fusion power generation on Earth, let alone developed a functioning fusion rocket. The reasons why reveal fundamental challenges that suggest fusion propulsion may remain forever in the realm of proposals rather than reality. The basic principle of fusion is straightforward. Force light atomic nuclei, typically isotopes of hydrogen like deuterium and tritium, to merge together, releasing energy in the process. This is what powers stars, including our Sun. The challenge is that atomic nuclei are positively charged and repel each other electromagnetically with tremendous force. To overcome this repulsion and force nuclei close enough to fuse requires extreme conditions, temperatures of tens of millions of degrees Celsius and immense pressures. In stars, gravity provides the pressure to confine hydrogen at these temperatures for fusion to occur. On Earth, we don't have stellar mass gravity, so we must use other methods to confine and compress the fuel. After 70 years of intensive research and hundreds of billions of dollars invested, we've built machines that can briefly achieve fusion reactions, but we still can't extract more energy from fusion than we put in to make it happen, the break-even point that must be exceeded for fusion to be a useful power source. The two main approaches to fusion on Earth are magnetic confinement fusion, exemplified by tokamak reactors like ITER, currently under construction in France, uses powerful magnetic fields to contain a plasma of hydrogen isotopes at temperatures exceeding 100 million degrees Celsius. The magnetic fields keep this hellishly hot plasma from touching the reactor walls, which would instantly cool it and stop the fusion reactions. Tokamaks have achieved fusion reactions and even approached break-even conditions, but sustained controlled fusion that produces net energy output has remained elusive. The plasma is extraordinarily difficult to control. It develops instabilities, experiences turbulence, and finds ways to leak energy faster than fusion can produce it. ITER, with a construction cost approaching $25 billion, aims to finally achieve sustained net energy output, but it won't be operational until the 2030s at the earliest, and even then it's an experimental reactor, not a practical power plant. Inertial confinement fusion takes a different approach. Use powerful lasers or particle beams to compress a tiny pellet of fusion fuel so rapidly that it achieves the temperatures and pressures needed for fusion before it can fly apart. The National Ignition Facility in the United States, with 192 powerful lasers focusing on targets smaller than a peppercorn, has spent decades working towards achieving ignition, the point where the fusion reaction becomes self-sustaining and releases more energy than the lasers delivered to the target. In December 2022, NI finally achieved this milestone for the first time, producing about 1.5 times more fusion energy than the laser energy delivered to the target. This was celebrated as a breakthrough, and it was scientifically. But practically, it doesn't solve the fusion power problem. The lasers themselves consumed about 300 times more electrical energy than the fusion yield. The overall efficiency from wall plug electricity to fusion energy was less than 1%, and this was for a single shot. The facility can't repeat this continuously to generate sustained power. Now, imagine trying to put fusion reactors on a spacecraft. All the challenges that make fusion difficult on Earth become vastly worse in space. A tokamak-style magnetic confinement reactor requires superconducting magnets cooled to near absolute zero to generate the powerful fields needed to contain the plasma. These magnets are enormous, heavy, and require complex cryogenic cooling systems. ITER's magnets weigh thousands of tons. The reactor vessel itself is a massive structure designed to withstand the intense neutron radiation produced by fusion reactions, neutrons that stream out of the plasma and gradually damage any material they hit. On Earth, we can build thick shielding and regularly replace damaged components. On a spacecraft, every kilogram counts, and there's no possibility of replacing irradiated reactor components. The reactor must function flawlessly for decades while being bombarded by neutrons that make its materials brittle and radioactive. The thrust extraction problem is equally daunting. In a terrestrial fusion power plant, the energy from fusion reactions heats a working fluid, probably water or molten salt, which drives turbines to generate electricity. This is fundamentally a thermal cycle, and thermal cycles are inherently inefficient. Even the best turbines only convert about 40 to 50% of heat energy into electricity. The rest must be radiated away as waste heat. On a spacecraft, radiating waste heat is extremely difficult because radiation is the only available cooling mechanism. There's no air or water to use for cooling. You'd need enormous radiator panels, adding more mass and complexity. Then you'd use the electricity to power some kind of electric propulsion system, probably ion drives or plasma thrusters, which introduces more efficiency losses. The compounded inefficiencies mean you're converting perhaps 20 to 30% of your fusion energy into actual thrust, assuming everything works perfectly. Direct fusion propulsion attempts to bypass these efficiency losses by using the fusion exhaust directly as rocket thrust. Concepts like the direct fusion drive propose channeling the high-energy particles produced by fusion reactions out through a magnetic nozzle to generate thrust directly. This is more efficient in principle, but it requires controlling and directing a plasma at temperatures of hundreds of millions of degrees with extraordinary precision. The magnetic nozzle must focus this plasma without allowing it to touch any physical surface. Touching the nozzle walls would instantly vaporize them and destroy the engine. The engineering challenges here exceed anything we've attempted. We're talking about a rocket engine where the exhaust is so hot that it exists as a state of matter, plasma, that can only be controlled by invisible magnetic fields, and any loss of control means catastrophic failure. The fuel for fusion rockets presents its own challenges. The easiest fusion reaction to achieve is deuterium-thorium fusion, which occurs at relatively lower temperatures than other fusion reactions. Deuterium is stable and relatively abundant. It can be extracted from seawater. But thorium is radioactive with a half-life of only 12.3 years, meaning half of it decays away every dozen years. There are no natural sources of thorium in significant quantities. It must be manufactured in nuclear reactors at great expense. For a multi-decade interstellar mission, carrying thorium fuel means watching a substantial fraction of it decay into helium-3 before you even need it. You'd have to carry extra fuel to account for this decay, but thorium is also difficult to store. It's a gas at room temperature, so it must be kept under high pressure or cryogenically frozen, both of which require heavy tanks and cooling systems. One of the most ingenious concepts ever proposed for interstellar travel is the Bussard ramjet, conceived by physicist Robert Bussard in 1960. The idea seems to solve the fundamental problem that has plagued every propulsion concept we've discussed, the need to carry fuel. Why not collect it as you go? Interstellar space contains hydrogen atoms, and hydrogen can be used as fusion fuel. A spacecraft equipped with an enormous magnetic scoop could gather hydrogen from the interstellar medium as it travels, feed that hydrogen into a fusion reactor, and use the energy to continue accelerating. The spacecraft would be like a jet engine that breathes air, except it's breathing the tenuous hydrogen of space. You'd never run out of fuel, and the tyranny of the rocket equation would be defeated. Unfortunately, when you examine the actual numbers involved, the ramjet concept collapses under the weight of physics and engineering reality. The interstellar medium is so incredibly sparse that the cure becomes worse than the disease. Let's start with the fundamental problem: the density of the interstellar medium. In the space between stars, there's approximately 1 hydrogen atom per cubic centimeter on average. This might vary. In denser regions near stellar clouds, you might find 10 atoms per cubic centimeter. In voids, perhaps only 0.1 atoms per cubic centimeter. But 1 atom per cubic centimeter is a reasonable working estimate. To understand how sparse this is, consider that air at sea level on Earth contains approximately 10 to the 19 molecules per cubic centimeter. That's 10 billion molecules in the same volume that contains just 1 hydrogen atom in interstellar space. The interstellar medium is a better vacuum than anything we can create in laboratories on Earth. It's almost perfectly empty. Now imagine trying to use this near-nothingness as fuel.
For a fusion reactor to work, it needs a certain amount of fuel per unit time. Let's say our spacecraft's fusion reactor needs 1 kilogram of hydrogen per second to sustain the fusion reactions and produce useful thrust. With 1 hydrogen atom per cubic centimeter and each hydrogen atom having a mass of about 1.67 times 10 to the minus 24 grams, 1 kilogram of hydrogen represents approximately 6 times 10 to the 26 atoms. To collect this many atoms, the ramjet scoop would need to sweep through 6 times 10 to the 26 cubic centimeters of space per second. That's 600 trillion cubic meters per second, a volume the size of a mountain passing through your collector every single second. The scoop would need to be traveling at very high speed to sweep through this much volume, but even at 10% of light speed, 30,000 kilometers per second, a spacecraft covers 30,000 kilometers of distance per second. To sweep through 600 trillion cubic meters, your scoop's cross-sectional area would need to be 20 billion square meters, or about 160 kilometers in radius. Your magnetic scoop would need to be 320 kilometers wide, wider than the distance from New York City to Philadelphia. A magnetic scoop 320 kilometers in diameter is not a spacecraft component. It's a megastructure that dwarfs anything humanity has ever built. The International Space Station, our largest space structure, spans about 109 meters, roughly 1/3000th the size. The magnetic fields needed to create such an enormous scoop would need to be generated by superconducting coils carrying tremendous currents cooled to near absolute zero. These coils would mass thousands or millions of tons, requiring their own support structures. The power needed to maintain the magnetic fields would be enormous, possibly exceeding the power output you're getting from the fusion reactor. And this entire structure would need to survive for decades of interstellar travel, maintaining its precise shape and magnetic field configuration despite radiation damage, temperature extremes, and the stresses of continuous operation. The engineering challenges exceed anything in our technological capability by orders of magnitude. But it gets worse. The scoop creates drag. As your spacecraft moves through the interstellar medium, every hydrogen atom it encounters exerts a tiny force on the magnetic field that deflects it. This is drag, analogous to air resistance on Earth, but arising from a different mechanism. Each atom you scoop up was initially at rest relative to the interstellar medium, and you must accelerate it to your spacecraft's velocity to use it as fuel. This requires energy. At low speeds, this drag is negligible, but as your velocity increases, the drag force increases proportionally. At a certain speed, the drag force equals the thrust you're getting from burning the collected hydrogen, and you can't accelerate any further. This maximum velocity depends on the efficiency of your fusion reactor and the configuration of your scoop, but calculations suggest it might be around 10 to 15% of light speed at best, and possibly much lower. You've built an impossibly huge structure to achieve velocities that we've already established make interstellar travel impractically slow. The drag problem is even more fundamental than it first appears. To collect hydrogen effectively, your magnetic field must extend far ahead of your spacecraft, creating a large collection volume. But this means the field is interacting with a huge volume of space, and every atom in that volume exerts drag on your field. Some calculations suggest that at relativistic speeds, the drag from the magnetic scoop could actually exceed the thrust from the fusion reactor by a substantial margin. In other words, the ramjet would slow itself down rather than speed up. It's like trying to breathe through a pillow. Yes, there's air in there, but the resistance is so great that you expend more energy trying to breathe than you gain from the oxygen. The ramjet might not just be impractical, it might be fundamentally self-defeating. There are additional problems with the fuel collection itself. The hydrogen atoms in the interstellar medium are neutral. They're just hydrogen atoms, not ionized plasma. To collect them with a magnetic field, you first need to ionize them by stripping off their electrons. This requires hitting them with high-energy radiation or passing them through an ionization region. Either approach requires energy and adds complexity. The magnetic field can only affect charged particles, so neutral hydrogen will pass right through your scoop unless you ionize it first. The ionization process must be extraordinarily efficient across a region hundreds of kilometers wide, operating continuously for decades without maintenance. We've never built anything remotely approaching this capability. Even if you successfully collect the hydrogen, it's not in a form ready for fusion. You've gathered a stream of extremely low-density ionized gas, essentially a very tenuous plasma. Fusion requires compressing this fuel to tremendous densities and temperatures. The compression and heating equipment would need to take this whisper-thin stream of atoms and transform it into a dense, hot plasma suitable for fusion reactions. This is like trying to create a bonfire from individual atoms of wood scattered across a football field. Technically possible in principle, but the energy required to gather and compress the fuel might exceed the energy you get from burning it. The fusion reactor would essentially be running on fumes, trying to extract useful energy from fuel that's arriving at an incredibly low rate.
When confronted with the impossibility of reaching Alpha Centauri within a human lifetime at achievable speeds, some turn to Einstein's theory of relativity as a potential savior. According to special relativity, time passes more slowly for objects moving at high velocities relative to stationary observers, a phenomenon called time dilation. For astronauts traveling at speeds approaching the speed of light, subjective time aboard the spacecraft would pass more slowly than time on Earth. At 90% of light speed, time aboard the ship would pass at less than half the rate of Earth time. At 99% of light speed, the time dilation factor becomes dramatic, roughly 7 times slower. This means that a journey to Alpha Centauri that takes over 4 years from Earth's perspective might feel like only 7 months to the crew. At 99.9% light speed, the crew might experience the journey as lasting mere weeks. This sounds like the solution we've been seeking. The travelers could reach Alpha Centauri within their subjective lifetimes, perhaps even within what feels like a reasonable journey time. But this apparent solution is an illusion that creates as many problems as it solves, and it does nothing to address the fundamental impossibility of achieving these speeds in the first place. First, and most importantly, time dilation doesn't reduce the energy requirements for reaching relativistic speeds. It dramatically increases them. As you approach the speed of light, relativistic mass effects mean that accelerating your spacecraft requires exponentially more energy. At 90% of light speed, our 1,000 kilogram probe has a relativistic mass increase factor of about 2.3, meaning it effectively masses 2,300 kilograms from the perspective of acceleration. At 99% of light speed, the factor is about 7. Your spacecraft effectively masses 7 times more. At 99.9% light speed, the factor exceeds 22. The closer you get to light speed, the more the energy requirements explode toward infinity. We've already established that reaching even 10% of light speed requires energy equivalent to days of humanity's total power output. Reaching 90% light speed would require hundreds or thousands of times more energy. Reaching 99.9%, where time dilation becomes dramatic enough to compress years into weeks, would require energy investments so vast they have no practical meaning. We're talking about significant fractions of the total energy output of our sun.
Even if we somehow solve the energy problem, time dilation creates a psychological and social catastrophe that makes the journey essentially pointless from any human perspective. Yes, the crew experiences only 7 months subjectively while traveling at 90% of light speed to Alpha Centauri, and another 7 months returning. From their perspective, they've been gone about 14 months. But on Earth, over 9 years have passed, 4.86 years for the outbound journey, 4.86 years for the return. Everyone the crew knew has aged 9 years. Children have grown up, parents have grown older or passed away, careers have progressed without them. The world has changed. The astronauts return to a planet that's nearly a decade further in the future than when they left, while they've aged little more than a year. They're temporal exiles, strangers in a world that moved on without them. At more extreme velocities, where time dilation becomes more pronounced, the disconnection becomes total. Travel to Alpha Centauri and back at 99% of light speed might feel like 14 months to the crew, but Earth experiences nearly 19 years of elapsed time. Travel at 99.9% light speed might take only several weeks from the crew's perspective, but Earth ages by over 18 years. The astronauts would return to find everyone they knew profoundly changed or gone entirely. Friends who were in their 20s when the crew departed are now approaching middle age. Parents who were in their 60s are now dead or infirm. The entire social context that defined the crew's lives has evaporated. They haven't traveled through space so much as they've traveled into the future, skipping nearly 2 decades of history. This isn't exploration, it's voluntary exile from your own time period. For a one-way mission, time dilation makes the separation even more absolute. If the crew travels at 99% light speed to Alpha Centauri, the journey feels like 7 months to them, but takes 4.4 years from Earth's perspective. They can send messages back to Earth, but those messages take 4.4 years to arrive. By the time Earth receives the first message saying we've arrived safely, the crew has been at Alpha Centauri for 4.4 years by Earth clocks, but only about 7 months have passed for them. The temporal asynchrony makes communication surreal. Earth sends a reply saying, "Congratulations on your arrival," but that reply takes another 4.4 years to reach Alpha Centauri. Nearly 9 years after launch by Earth's timeline, the crew, who have subjectively experienced perhaps a year and a half, receive a message about an arrival that happened 7 months ago from their perspective. The conversation has a delay of nearly 9 years per exchange, and the delays are complicated by time dilation effects that make the timing even more disorienting. The psychological implications of time dilation are profound and disturbing. The crew knows with absolute certainty that they are traveling into Earth's future. Every moment that passes for them, multiple moments are passing on Earth. They can watch their homeworld aging faster than they are, moving further away from them not just in space, but in time. This creates a unique form of existential dread that no human has ever experienced. Astronauts on the Moon, or ISS, are separated spatially but exist in the same temporal frame. When they look at Earth, they're seeing it as it exists in essentially the same moment they're experiencing. Relativistic astronauts would look back at Earth knowing they're seeing it as it was years ago, that everyone they see through their telescopes has already aged years beyond that image, and that with every passing day aboard the ship, months or years are passing on Earth. It's like watching a time-lapse video of your entire life being left behind, knowing you can never return to the time period you departed from. Time dilation also creates bizarre scenarios around mission planning and communication. Suppose Earth sends a second, faster mission after the first. With advancing technology, perhaps the second mission travels at 99.9% light speed, while the first traveled at 90% light speed. The second mission might actually arrive before the first, despite launching later, because its higher velocity more than compensates for the delayed start. Now you have crews arriving out of order, carrying messages from different time periods on Earth. The later crew might arrive carrying news of events that the earlier crew, still in transit, doesn't know about yet. The temporal coordination of multiple missions becomes an absurd puzzle where launch order and arrival order become disconnected. Despite everything we've discussed, the impossible distances, the unsurmountable energy requirements, the deadly radiation, the centuries-long journey times, the communication delays, the navigation precision, the life support challenges, and the fundamental limitations imposed by physics itself, humanity continues to dream about reaching Alpha Centauri and other stars. This persistence might seem irrational given the overwhelming evidence that interstellar travel is effectively impossible with any foreseeable technology. Yet this dream endures in our collective imagination, inspiring scientists, engineers, artists, and ordinary people who gaze up at the night sky. Understanding why we keep dreaming despite impossibility tells us something profound about human nature and our relationship with the cosmos. Perhaps more importantly, the pursuit of this impossible goal has driven genuine progress in technologies and scientific understanding that have practical value even if the ultimate dream remains forever out of reach. The human impulse to explore is deeply woven into our evolutionary history and cultural identity. Our species didn't remain in the African savanna where we evolved. We spread across the planet, crossing oceans, traversing deserts, climbing mountains, and settling in every environment Earth offers. When European explorers crossed the Atlantic, they faced journeys lasting months with significant chances of death, uncertain destinations, and no possibility of quick rescue. Many expeditions failed catastrophically, yet people kept going because exploration is fundamental to who we are as a species. The unknown calls to us with a voice that defies rational calculation of costs and risks. When we look at stars like Alpha Centauri and know that planets orbit there, worlds we can detect but never visit, the frustration is almost physical. We're faced with the ultimate frontier that our evolutionary drive to explore cannot overcome, and this creates a psychological tension that refuses to accept impossibility.
This drive manifests in how we've approached the problem. The Voyager missions, while not aimed at any particular star, carry golden records with sounds and images of Earth, messages to potential alien civilizations or future humans who might somehow retrieve these artifacts millions of years hence. We know rationally that the odds of anyone ever finding these records approaches zero, yet we send them anyway. The gesture matters. Breakthrough Starship, despite its formidable challenges, received funding and continues to be seriously studied by reputable scientists. NASA has funded studies of advanced propulsion concepts, including fusion drives, antimatter systems, and exotic physics proposals. These efforts continue not because success is likely, but because the attempt itself has value. Working on impossible problems sometimes yields unexpected breakthroughs in adjacent areas. The Apollo program, while ultimately successful, was motivated partly by competition and national pride, not entirely rational drivers. Yet it produced technological advances that transformed telecommunications, material science, computing, and numerous other fields. The pursuit of interstellar travel has already pushed forward multiple technological frontiers, even though we're nowhere near achieving the goal itself. Research into ion propulsion, driven partly by dreams of deep space exploration, has produced practical engines now used on missions throughout our solar system. The Dawn spacecraft used ion drives to visit both Vesta and Ceres, something impossible with chemical rockets. Solar sail technology, inspired by concepts for reaching nearby stars, has been demonstrated on missions like Icaros and the Planetary Society's Light Sail, opening up new possibilities for propulsion within our solar system. Research into closed-loop life support systems, motivated by the requirements of long-duration missions, has applications for sustainable living on Earth and could help with challenges like providing clean water and recycling resources in remote or resource-limited areas. Advanced materials research driven by the need for ultra-lightweight, strong, radiation-resistant materials for interstellar spacecraft has produced materials useful for everything from aviation to medical devices. The study of interstellar travel has also deepened our understanding of fundamental physics. Analyzing what would be required to reach relativistic speeds has led to better understanding of relativistic mechanics, radiation physics, and the behavior of matter under extreme conditions. Theoretical work on exotic propulsion concepts, wormholes, warp drives, negative energy, has pushed the boundaries of general relativity and quantum field theory, even though these concepts almost certainly remain in the realm of science fiction. Sometimes studying impossible things reveals why they're impossible in ways that illuminate deeper truths about the universe.
We now understand the cosmic speed limit and why it exists more deeply than Einstein could have imagined, partly because we've seriously studied what it would take to approach that limit. There's also a philosophical dimension to why we keep dreaming about interstellar travel, despite its impossibility. Accepting that we might be permanently confined to our solar system forces us to confront our cosmic significance, or lack thereof. Humans have consistently overestimated our importance in the universe. We thought Earth was the center of everything until Copernicus. We thought our sun was special until we understood it's one of hundreds of billions of stars. We thought our galaxy was the entire universe until we discovered it's one of hundreds of billions of galaxies. At each step, our cosmic significance diminished. But we consoled ourselves with the idea that someday we'd spread among the stars, that our descendants would inhabit countless worlds, that humanity's future was unbounded. The realization that we might be forever trapped in one tiny stellar system, unable to reach even our nearest neighbors, is a final diminishment that's psychologically difficult to accept. Yet this confinement isn't as limiting as it first appears. Our solar system is vast beyond comprehension by everyday standards. From the sun out to the heliopause, where the solar wind meets interstellar space, is about 120 astronomical units, roughly 18 billion kilometers. The Oort cloud, the outermost region of the sun's gravitational influence, extends perhaps 100,000 AU, or roughly a quarter of the distance to Alpha Centauri. Within this volume, we have 8 planets, dozens of major moons, hundreds of thousands of asteroids, billions of comets, and uncounted smaller objects. Many of these worlds are scientifically fascinating. Europa and Enceladus might harbor subsurface oceans with conditions suitable for life. Titan has lakes and rivers of liquid methane, a complex organic chemistry, and weather patterns. Mars might have once been habitable and could tell us whether life arose independently elsewhere. The asteroids contain resources and could someday support mining and manufacturing. Even if we're confined to our solar system, there are lifetimes worth of exploration ahead, destinations that are actually reachable with existing or near-future technology. After confronting the harsh reality of why reaching Alpha Centauri is impossible, it's easy to feel defeated, as if humanity's cosmic ambitions must be abandoned entirely. But this would be a mistake. While interstellar travel may forever remain beyond our grasp, there's an entire solar system around us waiting to be explored, and technologies emerging that will let us study distant worlds in ways our ancestors could never have imagined. The question isn't whether we can physically reach Alpha Centauri, we've established we cannot, but rather what we can actually accomplish within the boundaries that physics imposes. The answer is far more encouraging than the impossible dream of interstellar travel might suggest. Our own solar system represents a frontier that will take centuries or millennia to fully explore. And unlike Alpha Centauri, it's actually accessible. Robotic spacecraft have already visited every planet, numerous moons, asteroids, and comets. But these have been brief flybys or short-term missions. The next phase of solar system exploration involves sustained presence, permanent bases, long-term monitoring, detailed study of environments we've only glimpsed. Mars in particular offers realistic goals that challenge our capabilities without requiring impossible physics. Humans could potentially walk on Mars within the next few decades. The journey takes 6 to 9 months with current propulsion technology. Long and difficult, but within the range of what we know how to do. Unlike an interstellar mission, a Mars expedition has abort options, communication delays of just minutes, and the possibility of return. The engineering challenges are immense, but solvable. Radiation shielding for the journey, life support systems for the surface habitat, in situ resource utilization to produce fuel and oxygen from the Martian atmosphere, and sustainable food production. None of these problems require new physics. They require engineering, investment, and commitment.
Beyond Mars, the outer solar system offers destinations that are scientifically compelling and physically reachable. Europa, Jupiter's moon, probably harbors a global ocean beneath its icy crust containing more water than all of Earth's oceans combined. This ocean has been liquid for billions of years, warmed by tidal heating from Jupiter's gravity. It might contain life, organisms that evolved entirely independently from Earth life, proving that biology isn't unique to our planet. A mission to Europa would be extraordinarily challenging. The journey takes years, Jupiter's radiation environment is brutal, and drilling through kilometers of ice to reach the ocean would require technologies we're still developing. but crucially, it's possible. NASA's Europa Clipper mission, launching the 2030s, will conduct detailed reconnaissance. Follow-up missions could land on the surface and eventually breach the ice. This isn't science fiction. It's engineering that we can actually do, given sufficient resources and time. Enceladus, Saturn's small moon, presents similar opportunities. The Cassini spacecraft discovered geysers erupting from Enceladus's south pole, shooting water and organic molecules into space. This moon has a subsurface ocean in contact with the rocky core, conditions that on Earth would almost certainly harbor life. A mission to Enceladus could fly through these geysers and analyze their chemistry directly, without even landing on the surface. The spacecraft could search for amino acids, complex organic molecules, or even cellular structures. Within our lifetimes, we might answer one of humanity's most profound questions. Are we alone in the universe? Not by traveling to another star system, but by visiting a small moon in our own cosmic neighborhood. Titan, Saturn's largest moon, is perhaps the most Earth-like world in the solar system, despite being radically different from Earth. It has a thick atmosphere, weather, seasons, lakes, rivers, and a complete hydrological cycle. Except the liquid is methane and ethane rather than water, and the temperature is minus 180 degrees Celsius. Titan's organic chemistry is extraordinarily complex, potentially representing a preview of the chemistry that led to life on early Earth. NASA's Dragonfly mission, a nuclear-powered drone that will fly through Titan's atmosphere and land at multiple sites, launches in the 2030s, and will revolutionize our understanding of organic chemistry and potentially prebiotic processes. This mission uses technology we have today: radioisotope power sources, autonomous navigation, and spacecraft engineering refined over decades. It's ambitious but achievable, offering scientific returns that rival anything we might learn from Alpha Centauri. While robotic probes explored the physical world of our solar system, telescopes are revolutionizing our ability to study worlds we cannot reach. The James Webb Space Telescope, launched in 2021, can analyze the atmospheres of exoplanets by watching starlight filter through them during transits. By examining which wavelengths are absorbed, astronomers can determine atmosphere composition, detecting water vapor, carbon dioxide, methane, and potentially biosignature gases like oxygen and phosphine. Future telescopes, even more powerful, are being designed specifically for exoplanet characterization. These instruments might detect not just the presence of atmospheres, but their detailed chemistry, temperature structure, weather patterns, and possibly even hints of biological activity. We might detect chlorophyll signatures in the light reflected from an exoplanet surface, indicating photosynthetic life. We might measure seasonal variations in atmosphere composition that suggest biological processes. We could potentially discover life on planets around Alpha Centauri or thousands of other stars without ever leaving Earth orbit. Ground-based telescopes are also advancing rapidly. The extremely large telescope, currently under construction in Chile, with a 39-meter mirror, will be able to directly image large exoplanets and characterize their atmospheres. Arrays of radio telescopes can combine their signals through interferometry to achieve effective apertures spanning continents or even the entire Earth. Future space-based interferometers could use multiple spacecraft flying in precise formation to create effective telescope apertures thousands of kilometers across, achieving angular resolution sufficient to see continents and oceans on exoplanets dozens of light years away. We might create maps of worlds around other stars, identifying oceans, land masses, ice caps, and cloud patterns. We could watch weather systems evolve, track seasonal changes, and observe these worlds over decades to understand their climates. All of this from the comfort of our own solar system, without requiring impossible propulsion systems or centuries-long journeys. The long-term future, centuries or millennia ahead, might see humanity undertaking mega-scale engineering projects within our solar system that would have seemed like fantasy to previous generations. Dyson swarms, vast arrays of solar collectors surrounding the sun to capture significant fractions of its energy output, could provide power measured in petawatts or even more, perhaps enough to seriously consider some of the more extreme propulsion concepts we've discussed.
Orbital habitats could house billions of people in engineered environments, offering Earth-like conditions with controlled weather, no natural disasters, and efficient use of resources. Mining the asteroid belt could provide raw materials for construction projects on scales impossible on planetary surfaces. Over millennia, humanity might engineer significant portions of our solar system, creating a civilization far more capable than today's Earth-bound society. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.